Hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Stepping inside as we jump into section 3.6 in the Big Ideas Math Integrated Math 3 textbook. This section is called the Fundamental Theorem of Algebra. Sounds pretty important, right? Well, it kind of is. So we're going to dive into this right now. If you want to jump into the description section down below and find specifically what you're looking for, download the PDF or find the problem set as I begin with the lecture portion. It's up to you on what you want to find. You can go ahead and find that there. And I will get started in 3, 2, 1, go. You'll learn to use the Fundamental Theorem of Algebra. Sounds pretty important. Find conjugate pairs of complex zeros of polynomial functions. So complex also, when we're thinking of imaginary solutions, things with I are kind of what we're thinking about when we hear that. And use Descartes' Rule of Signs. Okay, complex conjugates, once again, is the new core vocab. Now, in the last section, I wasn't sure if they assumed that you were supposed to know how to do those or not. So there were a couple problems, I think, on the later end where I was like, let's solve the ones for I as well, shall we? I didn't spend too long talking about how to do it. I was just doing it. Square roots of negatives. So I imagine we're going to be getting them here. And we will, as we talk about the Fundamental Theorem of Algebra. The table shows several polynomial equations and their solutions, including repeated solutions. So here you have a linear equation 2x minus 1 equals 0, quadratic x squared plus 2 equals 0, and a cubic x cubed plus x squared minus x minus 1 equals 0. Different degrees of these polynomials and these solutions that you get from them. Now, when you solve for x here, you add 1, divide by 2, you just get 1/2 as an answer. This one you have to subtract 2. Let me kind of write it. You get x squared equals negative 2, and then take the square root of both sides, and that's where you get plus or minus I root 2. That's, again, taking square root of a negative. Again, the book, for some reason, you can tell it's off-center. The book, for some reason, the digital version never shows the plus or minus. I don't know why. But that's two solutions. That's two solutions. There's positive I root 2 and negative I root 2. They may be imaginary, but they are those solutions. I'm not going to dive into actually solving this one here. You can try and plug in the numbers. They do work. But the fact is, I guess the way that this thing factors, to get solutions of -1, -1, and 1, because they talked about repeated solutions, is that this must have been x plus 1 quantity squared times x minus 1. When you use zero product property, you get 2 instances of it. So there's a repeated solution there. That means there are 3 solutions total if you include the repeated solution. Now, in the table, note the relationship between the degree of the polynomial and the number of solutions. 1 degree is 1 solution, 2 is 2, 3 is 3. Can you prove by example? No. Are they supporting what they're talking about with examples? Yes. This relationship is generalized by the Fundamental Theorem of Algebra. So here's the theorem and its corollary. The theorem states if you have a function that's a polynomial of degree n, meaning the largest degree, and it's greater than 0, meaning not a constant, something to solve x with, then the equation f of x equals 0 has at least one solution in the set of complex numbers. That means you are going to be able to solve something somewhere in any instance. You can find a value for x, real, imaginary, or otherwise, so long as it's a polynomial. You will cross the x-axis somewhere, basically, is the way we're saying it. The corollary, sorry, I shouldn't say you'll cross the x-axis. There are imaginary solutions that won't always necessarily make that so. The corollary is basically an extension of the theorem that also proves to be true. If f of x, and this is the more important one to us, if f of x is a polynomial of some degree n, it has exactly n solutions, provided each solution repeated twice is counted as 2 solutions and repeated 3 times is counted as 3 solutions. Now, when they say repeat solutions, you might have heard me in the last section, I call those multiplicities. So this one has a solution of -1, which has a multiplicity of 2. And then it has a solution of 1 with a multiplicity of 1. And 2 -1s and a 1 make 3. So a cubic should have 3 solutions always, including multiplicities. A quadratic should always have 2 solutions, including multiplicities. And a linear function should always have 1 solution. And you can also include, see, they say complex solutions. Number of complex solutions. That includes imaginary solutions, such as I. So all of those count. That's the Fundamental Theorem of Algebra, that the degree of the polynomial states how many solutions there will be. Now, I stated as much in the last section as well. It's something that I kept teasing and saying, this will show up in the next section, this will show up in the next section. Now it'll show up in this section, so I can keep rehashing what I was stating before. For example, if I have a quartic like this one, I'm expecting 4 solutions. Okay? So how many solutions does this have? I expect 4. Find all the solutions. Because it's degree 4, it has 4 solutions, as they stated. Notice you can use the factoring by grouping to solve this. I'm not going to get deep into that. That's what we were talking about before. But when you solve it, blah, 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 we get to factored form here. This does not factor anymore, but this one gets as deep as you can. You get x equals -2 and -1. The other two you can find they use the quadratic formula. I personally prefer completing the square for a situation like that. But you still get, ultimately, 1 plus or minus I root 3. Now remember, the plus or minus that seems to be missing in all these represents two different solutions now. There's 1 plus I root 3 and 1 minus I root 3. So there are 4 solutions total. This one, this one, this one, and this one. 2 of them are complex, 2 of them are real, and we move forward. Finding the zeros of a polynomial function, more of the same as before. When they say to find the zeros, it means set y equal to 0 and then solve for x. You have something here that is a quintic polynomial. Degree 5 would mean 5 solutions, so finding those zeros. Because this is not easily factorable in any sort of way, we're going to use the rational root theorem to attempt to solve. So the possible rational solutions, you take factors of 8 over factors of 1, and you get plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. You can check and find out what one of the zeros are. They find out -1 is a 0. You can plug in -1 here and find out you get 0. So we use synthetic division on -1 as a root, and you reduce this into, apparently, I don't know, I'm just going through their example. If you take x minus 1 out, I guess they're okay, they factored a little more than, they're not showing all the work. Same thing as I'm thinking, right? We already did that work before, we're going to keep doing it, but they're kind of rushing you. So they find out that this is the factored form of this. Okay. They use synthetic division to pull out the first x plus 1, and then they did something after that. I don't know what, but that's what they did. Now, that means that -1 is a solution. Let's see where they wrote that. -1 is a solution, but it is a repeated root because of this degree of 2. It has a multiplicity of 2, so there are 2 -1 solutions. There's an x minus 2, therefore x equals 2 is a solution. And then they have this x squared plus 4, which can't be factored down more. You can solve that pretty simply. You can take the square, you can subtract 4 and take the square root of both sides. You get plus or minus 2y. Now, they are revealing the factored form of that. If you do, of course, subtract or add 2y to both sides again, then that means that these factors can be written as x plus 2y times x minus 2y. We generally don't write those kinds of things because we try and, how do I say it? Our factors tend to just be of integers and real numbers, real rational numbers, basically. Things like that. So, yeah, but that's the factors. That's the complete factorization of this if you include the imaginaries. Anyway, the zeros also include plus or minus 2i. So those are 5 total solutions as a whole. They're showing the graph and the real solutions. Keep in mind, because x equals -1 has a multiplicity of 2, it's going to bounce off of that graph at -1. We learned this in the last section. It's going to cross through 2. Now, you don't see the -2i and 2i because it's part of the imaginary set that's not there. So only the real ones are touched. Multiplicity of 2 there. There's the bounce off, and 2 there. It's a 5-degree polynomial, so it's going to start in one way, finish the other direction. Because it's a positive leading coefficient, it's going to start down, finish up. And that's, sorry, you should probably see it. Yeah, start down, finish up. And that's exactly what we see right there. Okay. Complex conjugates. Now, what you've noticed in the past couple of examples here, you saw that there was plus or minus 2i. You saw 1 plus or minus whatever the other thing was as well. I root something. Every pairs of complex numbers of the form a plus bi and a minus bi, where b doesn't equal 0, are called complex conjugates. Every polynomial with real coefficients that have a conjugate, that have a complex number or imaginary solution will have a conjugate pair. So if there's an a plus bi, there will also exist an a minus bi. That's what will get them to cancel out. We saw the same thing when it came to the irrational conjugates as well, where you have a plus root b, there will also be an a minus root b. That's what gets them to cancel each other out in forms of multiplication. You don't want the irrationals, you got to have conjugate pairs. Same with this one here. So, using zeros to write a polynomial function, this will look like the same thing from the last section, only with conjugate complex conjugates instead of irrational conjugates. Write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and the zeros 2 and 3 plus I. So if 3 plus I is one of your solutions, then 3 minus I also must be one of them. That is its complex conjugate. So they do the same thing as they did last time. They write their factored form versions. You subtract the 2 over, you subtract 3 plus I over, you subtract 3 minus I over. They distribute the negative and then regroup it so that x minus 3 is the thing in parentheses here. So they can treat this as an a minus b times a plus b, which comes to be a difference of 2 squares, a squared minus b squared. Now I squared is negative 1. That's the part where that cancels, right? It's gone. I shouldn't say cancels, but it's no longer imaginary with respect to that. So subtracting negative 1 means plus 1. 9 plus 1 is 10. And you go to work distributing, you end up getting this polynomial. You can see it's all rational, real coefficients, leading coefficient of 1, all that jazz. You can double check by plugging in some things. I'm not going to be doing that unless they force it on me, but apparently you can still get 0 just by plugging in I. You can see all the work that's done in there to make that happen, and we're good to go. Okay, and the last thing I think we need to talk about here is Descartes' Rule of Signs. French mathematician René Descartes found the following relationship between the coefficients of a polynomial function and the number of positive and negative zeros of the function. Okay, if you have a polynomial function like this, really busy, and they have real coefficients, the number of positive real zeros is equal to the number of changes in sign of the coefficients of f of x, or is less than this by an even number. What they mean here is that as you go down your list in standard form, anytime your signs change from positive to negative and negative back to positive, etc., you count those number of changes. The number of changes that there are determines how many possible positive real coefficients that there are. You can have, if there are 5 sign changes, you can have up to 5. You couldn't have 4, but you can go down by 2s. You can have 5 or 3 or 1. If there were 4 of them, you could have 4 or 2 or 0. They go down by real amounts of 2, because if the other ones don't exist, they'd be imaginary or complex, whatever, and those would come in complex conjugate pairs. They have to go by 2s. And that's kind of why that is. Now, the number of negative real zeros is equal to the number of changes of the sign if the coefficients of f of negative x is or less than by this, or is less than this by an even number. I can't read, I'm sorry. Basically, plug in negative x into your thing and write out what your polynomial looks like. Look at the sign changes consecutively in standard form, descending order of degree. Goes from positive to negative, negative to positive. Count the number of changes that there are. And once again, if say there are 3 sign changes, then that means you can have up to 3 negative real solutions or 1, because you got to go down by 2s for the same thing. So using Descartes' rule of signs, let's look at an example. Determine the possible number of positive real zeros, negative real zeros, and imaginary zeros for f of x equals, and then you have this, I think they call it sextic function, with 6 degree, anyway, 6 degree polynomial. So what they're going to do is they're going to do it in a table, and the basic thing is, understanding the fundamental theorem of algebra, you need to have 6 solutions in total. Some positive, some negative, some imaginary, or none positive, 6 negative, well, you know what I mean. Any combination of them has to still add to 6. That would include multiplicities. I don't know if we're really getting to that. We're just talking about sign changes. We're not actually going to solve it. We got to figure this out. So when you look at f of x, the original function here, you can see that the first x to the 6th is positive. Now, when it goes from positive to negative, that's 1 sign change. When it goes from negative to positive again, that's 2 sign changes. And negative to positive again, that's, positive to negative is 1, negative to positive is 2, positive to negative is 3. Then it stays negative the rest of the way. That means there are no more sign changes after that. There are 3 total sign changes. That means the number of positive solutions there can be are up to 3, or there could be 1. Oh, what is that commercial thing I'm thinking of? You can either, oh my gosh, what was it? You can either go to 6 stores or just 1. Oh, I cannot remember what that is. Someone in the comment section tell me what that is. You can go to 5 or 6 stores or just 1. Oh, anyway. 3 or 1 positive real zeros. Okay. Now we're going to we're going to place those in a table in a bit in combination with the number of negative real zeros. How did they get 3 or 1 from negatives? Because they substituted negative x into here. And what happens when you raise negative numbers to an even power? It becomes positive. Negative numbers to an odd power stay negative, but subtracting a negative turns positive here. Remember, it was negative the first time. Now it's a plus. This one stays positive with the plus. This one turns negative, but with that minus is plus. This negative stays positive, but with a minus. Negative with the negative is a positive, and that's just a constant. So there are 3 sign changes again. These are all positive, 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 positive. The first sign change from positive to negative is 1. negative to positive is 2, positive to negative is 3. So 3 sign changes means you can have up to 3 or down to 1, negative 0. You can't have 0 of them, in this case apparently. You can't have 2. You can't have more than 3. So what they do is they make a table. They say, okay, imagine that 3 of them were actually positive and 3 were negative because you could have up to that many. That already adds to 6 itself. So now there will be 0 imaginary solutions. Therefore, there's the 6 total. Remember, these numbers always have to add to 6. If there was if there were 3 positive zeros and 1 negative 0, that's 4. But because the fundamental theorem of algebra and its corollary, you know there needs to be 6 total. Therefore, there will be 2 imaginary zeros in that case, with I in it, basically. Remember, these must come in conjugate pairs. That's the reason why these must go down by 2s. So this number must always be even. I'm just going to say that straight up. If this was 1 and this was 3, this would also be 2 here. And if these only had one of these each, then there would be 4 total imaginary zeros. I'm guessing there are probably some problems where we're also going to get into that notion of solving after coming up with the set, and then basically confirming it landed on one of these sets. Remember, if you have 3 of these, that means you could have even a multiplicity of 3 in that scenario. That still counts. All right, another example of real-life application. A tachometer measures the speed in RPMs at which an engine shaft rotates. For a certain boat, the speed x in hundreds of RPMs of the engine shaft and the speed s in miles per hour of the boat are modeled by this. What is the tachometer reading when this boat travels 15 miles per hour? So s is in miles per hour. We'd substitute 15 for s. And then you want to set equal to 0, so subtract 15 over here. That's why this number turns into this. So they're setting that equal, and they're going to solve for x. Looks like it's a good graphing calculator question. So the related function is to the equation is this. If you plug this into the calculator, you can take a look at its graph. By Descartes' Rule of Signs, you know f has 3 or 1 positive real zeros because there's a sign change from positive to negative here, 1, negative to positive here, 2, positive to negative here, 3. So it can be 3 or 1. We only care about the positive real zeros because we only care about positive RPMs. And I guess, by extension, positive speed. So, yeah, negative real zeros and imaginary zeros don't make sense in the context of speed. We couldn't care less about those ones. So you don't need to check for them. We only look at these other ones. So we go to the graphing calculator, which could do more than just this. But this one here, we find a positive where it crosses at a 0 of 19.8, what have you. Right? I don't think we're using really the rational root theorem to play with that one. It's going to take way too long. So graphing calculator, ahoy me hoy, we get about 19.86 hundreds of RPMs. They rounded apparently to 1990 RPM. Oh, because they rounded to 1 decimal place. That seems a little interesting because they have the precise value here. I would say 1986 RPMs, but you know, whatever. 1990 RPMs is good enough for me. And there's that guy. And that is the end of the lecture portion. So we're going to go ahead and go to the vocabulary and core concept check, and then we'll hit problems 3 through, I think, 53. So let's take a look at what we got. Complete the sentence. The expressions 5 plus I and 5 minus I are blank. These are known as complex conjugates. The idea, once again, is that when multiplied together in factored form, if you have x minus 5 plus I, x minus 5 minus I, like that, and multiplied together, you'll get all real coefficients as a result. These conjugate pairs will cancel each other out. These solutions always exist together in this way. How many solutions does the polynomial equation x plus 8 cubed times x minus 1 equals 0 have? Explain. You have 2 different ways to talk about this. You can solve for x in these things in factored form right now. You do get x equals negative 8 and x equals 1. You would be mistaken, though, if you said there were only 2 solutions. This one has a multiplicity of 3. It has a multiplicity of 3 because of this degree of 3 of the polynomial. So there are the true answers, if you wanted to write them out, are negative 8, negative 8, negative 8, and 1. I know it sounds weird to repeat the solution. That's why we generally don't do it. But as we've seen in graphing form, it behaves differently around that area. With this multiplicity, there are actually 4 solutions. So that's a reason that you can see there are 4 solutions. Another way is if you expand this, this would become x to the 4th. Eventually, if I expanded all of this, here it would become an x cubed plus something, times this x would become x to the 4th. So when expanded, the degree is 4. So that's another reason that you would come up with that. But here's the official multiplicity of 3. So 2 different ways to talk about it. This is really one to talk about within here, the solution set having a multiplicity 1, 2, 3, plus another one is 4. All right, guys, let's go ahead and get started with the official problem set now. If you're ready to go, we are going to be looking at all the stuff we had there. I know we rushed through some parts, but that's because it tailored to the previous sections or previous knowledge. So hopefully we can make sense of these here that we begin. In exercises 3 through 8, identify the number of solutions of the polynomial equation, then find all solutions of the equation. So in number 3, we have x cubed plus 64 equals 0. I do like that they're asking you to come up with how many solutions there are to begin with. Because it's a cubic, there will be 3 total solutions. Recall that multiplicities may be in place. Now, the thing that I would not do, and I'm going to write this in red, I would not subtract 64 from both sides and take the cube root of both sides. There's no problem with taking the cube root of a negative number, just as there's also not the problem with taking the square root of a negative number. The problem, only you'd get imaginary solutions. This would be negative 4. The problem is this isn't the only solution. We said there would be 3 solutions. And you might say, well, Mr. Robinson, no, it's negative 4 with a multiplicity of 3. That's not how multiplicities work. You need the factored form to be cubed of that thing to equal, that, right? If it was x cubed equals 0, 0 would have a multiplicity of 3, or x plus 4 cubed equals 0, negative 4 would have a multiplicity of 3, but not in this case here. No, what you instead have to identify your 3 total solutions is you actually here have a sum of 2 cubes. This is x cubed plus 4 cubed. And I'm not saying negative 4 isn't one of the answers, but there are 2 others that you are negating in this scenario. Now, the reason I write this out is because we need to factor this. This is a sum of 2 cubes. This factors into a plus b times a squared minus ab plus b squared. Now, x equals negative 4 is indeed one of the solutions. I never denied that, but there are 2 others. They're not negative 4. In fact, they're imaginary. I've mentioned before you can never factor this, and not only can you not, but these are complex solutions, and let's find them. They used quadratic formula in their set. I'm going to use completing the square. You can use whichever you so prefer, but I'm going to add something on this side that's not 16. I'm going to subtract the 16 over here. Divide negative 4 by 2 and square it. You get, not 2, you get 4. And this factors into x minus 2 quantity squared. Negative 16 plus 4 is negative 12. This is where we take the square root of both sides. Like I said, nothing wrong with taking the square root of a negative. Just know they are imaginary solutions. Root 12 is also 2 root 3. Square root of negative 12 is 2i root 3. Don't forget the plus or minus. I think you won't forget it when you keep in mind you still need 3 solutions. Here they are. Add 2 to both sides. X equals 2 plus or minus 2i root 3. So what are your 3 solutions? Negative 4, 2 plus 2i root 3, and 2 minus 2i root 3. Okay, that's your final set. That's what gives you your 3 solutions. That's why we don't stop at just that negative 4 there. I'm seeing a lot of problems in this set too, where I can do a debunking version of don't do this, instead do that. So let's go to this number 4 and talk about it the same way. Number 4. 8y to the 4th minus y equals 0. And I think the main thing that I want to bring up here is when in doubt, factor out. I don't know if I've ever said that phrase before. I say when in doubt, draw it out, but I've never done that. See, factor out. Don't divide. Don't do things like that early on. Here's what you don't do. Don't add y to both sides and then divide both sides by y and then get, 8y cubed equals 1 and go from there, taking the cube root of both sides and stuff like that. No. Even though here you could have a sum of 2 cubes, great, we're going to still talk about that sum of 2 cubes, but you just divided a y, you just canceled out one of your 4 solutions. This should have 4 solutions. You just got it down to 3 of them because you just got rid of one of them right here. So do not do that. No. Instead, do this. Don't divide y, you factor y. Y is a common factor here. Now you have 8y cubed minus 1. And from here, we can now continue our factorization of this. Keep in mind that is a difference of 2 cubes. This is 2y cubed minus 1 cubed, which, in terms of a cubed minus b cubed scenario, that factors into a minus b times a squared, squaring 2y is 4y squared, plus ab, 2y times 1, plus b squared, 1. So this is our factored form of this original problem. Okay, this is factored form. We have zero product property in use where y can equal 0. Or if 2y minus 1 equals 0, you add 1 to both sides and divide by 2. You get y equals 1/2. Here are 2 of your 4 solutions. We have 2 more. Here we can solve using quadratic formula or completing the square. This time I prefer quadratic formula. If you don't know the reason why, it's because this is a 4 instead of a 1. that definitely helps for me to use quadratic form instead. I'm going to apply the discriminant first here and work on b squared minus 4ac. Remember, you fully expect non-real solutions here. So this is going to be 4 minus 16, which is, once again, negative 12. We've seen that in the past. Now, when we are solving for these two, this will be y equals negative b plus or minus. We saw this before as 2i root 3, b squared minus 4, the square root of b squared minus 4ac, all over 2a. 2 times 4 is 8. So I might be rushing some of the quadratic formula stuff. The point of this lecture isn't to teach you quadratic formula, though. It's to see if you have kind of some mastery in that, or I'll do it for you, or you do the steps meanwhile as you move through it. Now, these can all divide by 2 to reduce these as a fraction. This would be negative 1 plus or minus 1i root 3, all divided by 4. So those are the other two solutions that will exist in this. Keep in mind, we did expect 4 of them total, not just 3. Here's 1. Here's the one you would have missed if you divided by y. But here's 1. Here's 2. Negative 1 plus I root 3 over 4 is 3. Negative 1 minus I root 3 over 4 is 4. So 4 total solutions on that. Now, number 5 is more of the same like number 4. Don't add t squared to both sides and then divide both sides by t squared to get rid of 2 of your solutions. Instead, what we're going to do, of course, is we're going to factor out that t squared. But t to the 6th minus t squared equals 0. First, anticipate how many solutions we're going to have. 6 of them in total. Thank you, Fundamental Theorem of Algebra, for saying what to expect. So, we do have a t squared common factor. You are left with t to the 4th minus 1. And this is a difference of 2 squares. This is quadratic form if you think of t to the 4th as t squared squared. So if factoring out the t squared, this can be t squared squared minus 1 squared. A squared minus b squared factors to a minus b times a plus b. So this factors into t squared minus 1 times t squared plus 1. And t squared minus 1 is its own difference of 2 squares, where it factors into t minus 1 times t plus 1. So we're getting this down to factored form. T squared plus 1 can't change, at least not as far as how we write factored form of real numbers within here. And now we can solve some of these here. If t squared equals 0, then t equals 0. However, this has a multiplicity of 2. Keep that in mind because that one is squared, that's what's going on there. If t minus 1 equals 0, then t equals 1. So here's the solution so far. T equals negative 1. And now we got to solve for this one. If t squared plus 1 equals 0, you subtract 1 from both sides. And then you take the square root of both sides. Now the square root of negative 1 is simply I. But given that we have so far 1, 2, 3, 4 solutions, remember 0 appears twice, we need 2 more solutions here. They should come in conjugate pairs. It's not just I that's the answer. It's plus or minus I. So t equals plus or minus I. Those are your 6 total solutions. 6 total solutions. You got 1, 2, 3, 4, plus I minus I, 5, 6. Okay, number 6. Z to the 4th plus 5z squared minus 14 equals 0. Once again, this is in quadratic form, meaning it's not a true quadratic, it's actually a quartic. But if we treat our z's instead of z as z squareds, we're squaring z squared here and stuff like that, we can then get our total of 4 solutions. I like that, once again, they have us anticipate it, so we know exactly what to look for with this. So we basically we'll factor it down to this, z squared times this, and z, whatever, plus this, z squared minus that. We got to find 2 numbers that multiply to negative 14 and add to 5. Those are 7 and negative 2. Now, neither of these are differences of 2 squares. Better yet, we have other conventions of solving these anyway. We can solve using square roots at this stage. Subtract 7 and take the square root of both sides. Here, you'll get plus or minus I root 7. Again, 2 solutions there. They're both complex. They come as complex conjugates. Z squared minus 2 equals 0. These will be real solutions, but irrational. Z equals plus or minus square root of 2. No I. Just irrational, though. There are plus or minus. So 1, 2, 3, 4 total solutions, as we expected. Number 7. Of course, they blend s's with 5s. There's no reason that they would ever not do that. I always complain about that because anytime there's an s, there will always be a 5. And it'll confuse you guys saying, wait, is that an s or a 5? And I go, well, I tried to write it as small as I possibly could for an s. And then I try and make my 5s look good. Look, I even tried to make my 1 actually look good there. All right, this is one that I can't factor by grouping, unfortunately. There is no common factor as well, so it looks like I'm going to rational root theorem, where I do factors of 1 divided by factors of 1. That leaves me with either 1 and or -1 to try. Let's try 1. 1 minus 1 minus 1 plus 1 equals 0. Okay, 1 works. At least it's an easy one. So we'll use 1 with coefficients of 1, -1, -1, and 1. Heck of a bunch of 1s. Don't even have to worry about s's and 5s right now, actually. Okay, so ultimately, when you factor out an s minus 1, I should say, when you factor out an s minus 1, you're then left with, oh, I made a mistake. Hold on. The fact that I had a 0 remainder means nothing actually here, because what did we have? A 0s to the fourth. Let's do that again. 0s to the fourth, -1s cubed, -1s squared, and 1. The only reason I actually caught on to that is because I saw there was a quadratic as a result, and using synthetic division doesn't bring you to a quintic to a sorry, it was probably a cubic. Doesn't bring you to that form. It's got to bring you to a quartic here. So, oh, I'm missing another one. Hold on. I'm totally off. Maybe that was a quadratic. All right, let's do that again. Jeez, man. Let's do it again. 1s to the fifth, 0s to the fourth, -1s cubed, -1s squared, 0s, and 1. Okay, now we're on that right track. Guys, super apologies. That never happens. I'm talking through the stuff so much that I just missed it. That's all. All right, did I make a mistake there? I don't think so. That should be good. Okay, so when you factor out the s minus 1 here, now you're left with 1s to the fourth plus 1s cubed plus 0s squared minus 1s minus 1. Now, this is one of those stages where, again, I still can't factor by grouping and no common factors. I got to try and plug in still rational roots. My only options still are -1 and +1. I can still try +1. 1 plus 1 minus 1 is still 0. So that still works. So given this, I'm going to use 1 again. Synthetic division. Let's not make a mistake this time. 1s cubed, 1s squared. 1s to the fourth, 1s cubed. 0s squared, -1s, and -1. Ooh, a 2? Okay. Okay. So another s minus 1 factors out. So I'll call this s minus 1 squared now. And this is now s cubed plus 2s squared plus 2s plus 1. Still can't factor by grouping. Still need to try and use rational root theorem. Only this time it doesn't appear that 1 will ever work because these are all positives. We can talk about Descartes' rule of these things, right? No sign change when these are positive. Therefore, there are no positive real solutions. But there are possibly negative ones. And -1 is possibly the one that we're talking about. So let's just try it. If it doesn't work, then there's really nothing else I could do. -1 actually just must be it. So I got a 1s cubed, a 2s squared, a 2s, and a 1. And let's go off that one. Okay, so from there, that is a -1. So now I have s minus 1 quantity squared times s plus 1. And the final factorization here is s squared plus s plus 1. Now, this is not factorable, but it is a quadratic. So I can solve going with, say, quadratic formula. In this case, I got the discriminant of b squared minus 4ac, or 1 minus 4, which is -3. That's what will go in the square root portion of the quadratic formula. S equals -b plus or minus the square root of b squared minus 4ac. Remember, you got to take the square root of that, so I root 3. All divided by 2 times 1, which is 2. These are the other two solutions outside of these ones right here, which I didn't yet write. There's s equals 1. This has a multiplicity of 2. And this is s equals -1, multiplicity of 1, standard. And we have these solutions here. Now, how many solutions did I expect? I didn't write it. I apologize. We expected, with a 5th degree, we expected 5 solutions. Let's count up how many solutions we have down below, see if we got them all. Apologies again on what I was doing here. Missing my zeros. I was talking so much over the stuff complaining about s's and 5s. I'm sure I just missed it. Anyway, I got 1, 2, 3, 4, 5. That's my version of Roman numerals, which didn't really work itself out. 5 total. We're good. All right, and number 8. Number 8 already looks easier than number 7 because number 8, it looks like I can use factoring by grouping, and so I intend to. So x cubed minus 3x squared plus 2x minus 6 equals 0. I expect 3 total solutions. I can factor this by grouping. I have x squared factoring out of the first two terms. You're left with x minus 3. I factor 2 out of the next two terms. I'm left with x minus 3. And in factoring these x minus 3's out from both these terms, I have x squared plus 2 on this guy. You can see that x equals 3 is one of your solutions. On this one, if x squared plus 2 equals 0, x squared would equal negative 2, and x would equal plus or minus I root 2. So there's use of zero product property. Those are the solutions. That was probably the quickest among all my answers I actually had to do, given that all these actually, yeah, that one's probably the quickest one. All right, cool. All right, next exercise is 9 through 16. Find all zeros of the polynomial function. So we already know what to expect for number of solutions. I won't write it, though I will, of course, say it out loud or remind ourselves of this is what I expected, and we'll be good to go. So it's a lot of what you were just doing previously, only these ones look a little more complex, probably a lot more rational root theorem. This problem already lends itself to looking like we're going to use that. So I expect 4 total solutions, including multiplicities, including complex conjugates, all that kind of stuff. So let's try and list our p's over q's for this one, and I won't do this every single time. This is just a reminder of one of them here. We're going to do factors of 8, 1, 2, 4, and 8, divided by factors of 1, 1. That leaves us with plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Now, a lot of times I try and plug in 1 and negative 1 by myself here before resulting to maybe some calculator work. Well, if I plug in 1, you get 1 minus 6, which is negative 5, plus 7, which is 2, plus 6, which is 8, minus 8, which is 0. So 1 works. F of 1 equals 0 means we have one of our rational roots right there. So let's use 1 on synthetic division with 1x to the fourth, negative 6x cubed, 7x squared, 6x, and negative 8. I feel like I have to say them out loud now because of the mistake I made on that 1. I never make that mistake, but there you go. I shouldn't say never because it happened. All right. Now this confirms with a 0 remainder that does indeed work out. So when I factor this out, this turns into, and by the way, I'm setting it equal to 0 now. They said find the zeros. We set y equal to 0. X minus 1 is one of the factors. The other factor is x cubed minus 5x squared plus 2x plus 8. Now we want to operate on this guy. Unfortunately, not factorable by grouping. So we are, once again, going to work off our factors of p over factors of q. Same set, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. If I try 1, it fails this time. Let's try negative 1. We get negative 1 minus 5 minus 2 plus 8. Negative 1 actually works. F of negative 1 equals 0. There's another check. So let's use synthetic division on negative 1 this time with 1, negative 5, 2, and 8. Do the same thing, break it down to a quadratic, and then we'll solve using other means after that. Well, quadratic formula, maybe it's factorable, something like that. This actually looks factorable, which is good, but let's keep going. If x minus 1 is a factor, x plus 1 is also a factor here. Not if. But then you have x squared minus 6x plus 8. And that's factorable. That factors to x minus 2 times x minus 4. Which means those were also possible. I could have plugged in 2 or 4 into those and done rational root theorem with those as well. So our final solutions are x equals 1, negative 1, 2, and 4. This was originally a quartic. I expected 4 solutions. We got 4 solutions. That's number 9. So listen, solving that question was technically no different than what we were doing in the last section. Everything that was involved in that question was fine. The difference in this section seems like we're going to get more complex solutions, and now we know what to expect for number of solutions and why. I might have mentioned those in the last section as far as what it was. Hey, if it's a quartic, I expect 4 solutions, but now we're really hearing it based on Fundamental Theorem of Algebra. So are these problems really different from the last section? No. If you got to solve using quadratic formula, completing the square or square roots for imaginary or irrational solutions, that might be really the only difference for you right now. This one, once again, no common factors, no factoring by grouping. We're going to use rational root theorem. Factors of 30 over factors of 1 give you, I'm not going to write them, but I'm going to try them plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. So if I start with 1, 1 plus 5 minus 7 minus 29 plus, let's see, 1 plus 5 is 6, minus 7 is negative 1 minus 1. I think 1 works. So if f of 1 equals 0, let's give it our shot. Okay. So here, yep. All right, so here, this now factors to x minus 1 times x cubed plus 6x squared minus 1x minus 30. Still not factorable by grouping. Let's set it equal to 0 actually now. So once again, rational root theorem with the same set. We still have plus or minus factors of 30. If I try 1 again, it doesn't work. Negative 1 also doesn't seem to work. I'll try 2 before, true negative 2 before I try and give in. 2 cubed is 8 plus 4 times that is 32 minus 2 minus 30. 2 does work. So f of 2 equals 0. Okay, so for 2, we're going to use it on this guy right here, okay? So we got 1x cubed, 6x squared, negative 1x, and negative 30. Okay, and we break it down to now this guy. So x minus 1 times x minus 2 times x squared plus 8x plus 15 equals 0. This is factorable to x plus 3 times x plus 5. And our final solutions there now are 1, 2, negative 3, and negative 5. 4 total solutions as expected. We are good. We are good. Okay, number 11. Number 11, same ugh as the ones before. I imagine most all of these, if not all of them. I'm going to take a quick peek and just tell you right now. I think number 12 we can factor by grouping. I don't think we can factor any of the other ones by grouping, at least from the onset, right, to begin with. Maybe after the first, just because we use rational root theorem for one time doesn't mean it needs to be used the next time. Depends on what the problem becomes after that. Anyway, expecting 4 solutions in this set, so I choose factors of 12, plus or minus 1, 2, 3, 4, 6, and 12. Okay, so I'm going to start with 1. 1 minus 9 is negative 8, minus 4 is negative 12, plus 12 is 0, so that works. G of 1 equals 0. So we'll go off of that. We're going to use 1 as a root. We got 1x to the 4th plus 0x cubed minus 9x squared minus 4x plus 12. So, here we go. All right, using synthetic division, we now can turn this into x minus 1 as the factor times we have x cubed plus x squared minus 8x minus 12 equals 0. Also still not factorable by grouping. We still have the same set here. We can try and plug in numbers again. 1 won't work. Negative 1 won't work. 2, we get 8 plus 4 is 12 minus 16. No. Negative 2 is negative 8 plus 4 is negative 4. Plus 16 is 12 minus 12 is 0. Negative 2 works. So G of negative 2 equals 0. That works. I'm glad I can do some of those in my head. I was resorting to calculator a lot before. You might be forced to use synthetic division, but again, you can plug in your numbers like I'm doing right there and it can work out instead of writing these all through synthetic division. Okay, so from here, we can go this. Okay. So from that, we get x minus 1 times x plus 2 times x squared minus x minus 6 equals 0. That last one is factorable into x minus 3 times x plus 2. Now, because x plus 2 was one of these already, I'm going to go ahead and square that factorization. It looks like another negative 2 could have come into the mix if you did rational root theorem, something like that. And 3 as well. So x equals 1, negative 2, and 3. Now, that only looks like 3 solutions to us, and we expected 4. However, negative 2 has a multiplicity of 2. So that makes our 4th solution. So that is our final set like that. Okay, number 12. Now, I stated number 12 appears to be factorable by grouping, and I stick to that. So we're going to factor by grouping. It is an x cubed, so 3 solutions are on the horizon. X cubed plus 5x squared minus 4x minus 20. We're going to set this equal to 0 as we factor by grouping. Take an x squared out of the first 2 terms, you get x plus 5. Take a negative 4 out of the next 2 terms, you get x plus 5. That's why this works. And then you're left with x squared minus 4 times x plus 5. Now, x squared minus 4 factors into x minus 2 times x plus 2. I always want to work out the difference of 2 squares whenever I can. And that leaves us with solutions of 2, negative 2, and negative 5. For some reason, I wanted to write that first. 2, negative 2, and negative 5. Those are your 3 solutions. That is a quick one of those problems, just like the number 8 from your. And I'm glad to have that one. However, as I projected looking onward, it does not appear that any of these other problems are factorable by grouping from the onset. So that was your one source of respite. We move. Number 13. Rational root theorem. We're going to do factors of 12, plus or minus factors of 12. Hopefully you're okay with me not listing them out, given that I'm trying upwards on these numbers to work it out. Now, all these are pluses. That means whether you're talking about Descartes' theorem or just whatever, Descartes' rule, whatever it's called, or not throwing shade at Descartes, or logic, no positive solutions can work here, only negatives. So I'm going to start with negative 1, see where I can go from there. We get 1 minus 4 is negative 3, plus 7 is 4, minus 16 is negative 12, plus 12 is 0. So negative 1 works. Negative 1 works is the first one to test. Remember, the only numbers I was going to test were negative 1, negative 2, negative 3, negative 4, negative 6, and negative 12. Those are the only possibilities. Okay, so g of negative 1 equals 0. Let's take a look. We got 1x to the 4th, 4x cubed, 7x squared, 16x, and 12. And we get this here. Okay. Ooh, good, good, good. What I see here is proportionality. 1 times 3 is 3. 4 times 3 is 12. That means, and all same sign, factorable by grouping will be allowed now. See? That's why I kept saying from the onset it's not factorable by grouping. So x cubed plus 3x squared plus 4x plus 12. This is factorable by grouping. I don't have to use rational root theorem here. Let's go ahead and turn this into factoring x squared out. I'm sorry. I just messed up one little thing and it undoes everything. Factoring x squared out, you're left with x plus 3. Factoring 4 out, you're left with x plus 3. Now that part factors to x squared plus 4 times x plus 3. Unlike the difference of 2 squares from before, this is not a sum of 2 squares. In fact, this has imaginary solutions. So x can equal negative 1. X can equal negative 3. And we got 2 solutions here. If you subtract 4 from, set this equal to 0, subtract 4 from both sides, take the square root of both sides, you get x equals plus or minus 2i. So 4 solutions for your quartic function. That is number 13. Number 14. Okay. Factors of 18 that we're going to try, plus or minus 1, 2, 3, 6, 9, 18. I think that's it. Yep. All right, let's try 1. 1 minus 1 is 0, plus 7 minus 9 is negative 2. Nope. Negative 1. 1 plus 1 is 2, plus 7 is 9, plus 9 is 18, minus 18 is 0. Yeah. So negative 1 works. I'm proud of myself. I haven't had to use the graphing calculator yet and plug in anything for one of those. So negative 1, synthetic division, away we go. Okay. That's an 18. That is a negative 18. That is terrible. Okay. I can do math, but I can't write. Okay. There's our zero remainder as confirmation of this. It looks like it's once again fact. Can you tell based on these numbers this will be factorable by grouping? I don't know if you've recognized over the course of time, if you've been following me whenever I say this looks factorable by grouping. This doesn't look factorable by grouping. I don't know if you can tell yet when it's supposed to be or not, but I can tell you it's factorable by grouping based on proportionality. Times -2 and times -2 is basically the thing. You're going to see some x minus 2's right here. So when you factor an x squared out of these, you have x minus 2. When you factor a 9 out of here, you're left with x minus 2. Basically, in a nutshell, I can technically do factor. I can go straight from this to this step I'm about to write now without the middle thing because of my recognition of what factoring by grouping provides. I tend to not want to for your guys' sake and don't want to make a mistake. A sum of two squares is no good for us when it comes to factoring, at least in a general case, but we do get -1 and 2. And if you've seen this a couple times, we're going to subtract 9 and take the square root. That'll be 3, but plus or minus 3 with an I on it. X equals plus or minus 3i. Those are the imaginary solutions there. 4 of them, it was a quartic. Numbers 15 and 16 are quintic, fifth degree functions. We expect 5 solutions on them. Unfortunately, factoring by grouping isn't a part of what we have here. So it's just a lot more work, basically, especially if rational root theorem has to be used over and over again. The problem is we're going to have to probably use it at least twice, unless this thing becomes some sort of quadratic form quartic. A quartic is an odd-termed polynomial at most. So we're probably going to have to do rational root theorem more than once. Let's try and plug in 1. 1 plus 3 is 4, minus 4 is 0, minus 2 is -2, not quite. -1, -1 plus 3 is 2, plus 4 is 6, minus 2 is 4, plus 12 is 16, minus 16 is 0. It works. All right. I feel proud. -1 works. Here we go. Got to fit all these. So 1, 3, -4, -2, -12, -16. All right, here we go. Okay, so we got to this guy here. This now factors to x plus 1 times x to the 4th plus 2x cubed minus 6x squared plus 4x minus 16. Okay. Once again, I want to try. So 1 won't work here if it didn't work the first time. -1 may work again. I want to try that first before going on to 2, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16. So let's try -1 again. We get 1 minus 2 is -1, minus 6 is -7, plus, okay, that doesn't work. Let's try 2. It's 16 plus 16 is 32, minus 24 is 8, plus, did I say 8? Plus 8 is 16, minus 16 is 0. I think 2 works. So for this one, we're talking about just this part right here, right? G of 2 is 0 in that case. So we're going to use 2 in synthetic division on that. I'll just do it in blue to not blind you too much. 1, 2, -6, 4, -16. Okay. Okay, and that's factorable by grouping going forward, which is awesome. So x plus 1 times x minus 2 times x cubed plus 4x squared plus 2x plus 8. Let's see if you can do this mentally with me, given that these are 4 times larger, right? If we factor out, hold on, check this out. If we factor out x squared from these two and 2 from these two, that's x squared plus 2, and inside you're left with, in both of them, x plus 4. Factor out x squared from here, you have x plus 4. Factor 2 from here, you get x plus 4. That's where that comes to be. I don't know if you can understand that that's how I did that factoring a little faster in that way, but that's how it works. Anyway, so your final solutions here, we are going to get -1, 2, -4, and here, what will you get? Let's write them out separately. Subtract 2, take the square root of both sides. That's I root 2 and -I root 2. That's plus or minus I root 2. Plus or minus I root 2. Those are the 5 solutions you have. You don't have to write them separately. I'm just giving you the list as 5 because I want to be different, right? Sometimes I just want to show you different versions of what you can do, how you can be more efficient, or where I can be faster for my own sake. And there it is. Remember, I'm guiding you. I can only show you the door. You're the one who has to walk through it, right? A little Morpheus Matrix motto. Do your work in between, right? I'm still stating out loud what it is that you do, and I hope that you can recognize what that is for what it is. Okay, a lot bigger numbers as a whole right here. I'll be fearsome if I have to plug in like factors of like 20 that are like 4 and 5 and stuff. So we're going to try plus or minus 1, 2, 4, 5, 10, and 20. I'll start with 1. 1 minus 20 plus 20 is back to 1. Minus 21 is negative 20 plus 20 is 0. So 1 does work. 1 does work. So keep in mind there's no x to the fourth term. So 1x to the fifth plus 0x to the fourth minus 20x cubed plus 20x squared minus 21x plus 20. Okay. At least the number is 1 that we're multiplying by as well. Keeps it nice and small. You can see why synthetic division rules all over. You don't want to use long division if you don't have to. And hopefully you've kind of learned that through the course of what we've been doing the last few sections. Okay. Not factorable by grouping. I think never was going to be. So this factors into x minus 1 times x to the fourth plus x cubed minus 19x squared plus 1x minus 20. When set equal to 0, we keep going. We can try 1 again. 1 plus 1 is 2, minus 19 is negative 18, plus 1 is negative... Wait, hold on. Did I say that right? 1 plus 1 is 2, minus 19 is negative 17, plus 1. Okay, well, I don't think that worked. Negative 1. That's 1 minus 1 is 0, minus 19 is negative 19, minus... Okay, that didn't work either. Hold on. Make sure the signs are right. Okay, I don't think negative 1 worked either. I'll try 2, and if that doesn't work, I think I'll succumb to the calculator. 2 to the fourth is 16, plus 2 cubed is 8, so it's 24. Minus 19 times 4 is minus 76. This is why I don't want to do it this way, because I forgot what I'm adding. 24 minus 76 is negative 56, plus 2. Okay, that doesn't work. Maybe negative 1 does work, and I'm missing the calculation in my head. I hope I didn't mess up the synthetic division process. I shouldn't have, since I got zeros. Let's just go to the graphing calculator and do the rest from there. So x to the fourth, I finally gave in on a problem, even though the next one is probably the one that it's going to be. X squared plus x minus 20. All right, let's confirm. Let's go and ask for bits. Let's confirm that 1 and negative 1 did not work. 1, negative 1. Okay, those didn't work. Okay, I feel better about myself. 2, okay. Negative 2 didn't work either. Okay, other factors of 20. 4 and negative 4. Okay, C4. So that would have taken a while to do for myself there, so I'm glad that I didn't really do it for much longer. 256 plus 64. Oh, that would have taken a while. All right, f of 4 equals 0. We still have to use synthetic division. Calculator did not give us everything. So we're going to use synthetic division on that. And we get this. And this looks factorable by grouping, very much so. This time I won't go the short route. I do want to really talk about common factors in this one, okay? So this will become x minus 1 times x minus 4. Remember, I'm bringing down this x minus 1. This is x minus 4. Now I have x cubed plus 5x squared plus x plus 5. So when it comes to factoring that one, what do we got? An x squared is a common factor here to get x plus 5. And remember, factor out a 1 here to get x plus 5 there. You must reveal what that one is for yourself so you know what term you're pulling out of there to make that happen, right? As x plus 5 is a common factor in both of those, you're left with x squared plus 1 in the other guy. So x squared plus 1 times x plus 5. So your solutions are 1, 4, negative 5. And if I list these two out, subtract 1, take the square root, that is plus or minus I. So I and negative I. Those are the 5 in this quintic polynomial, degree 5 polynomial. Okay, about an hour in, let's keep moving forward. Oh, there were 2 more problems on the bottom, I guess. Okay, I missed them. Numbers 17 and 18, or number 17 to 20, determine the number of imaginary zeros for the function with the given degree and graph. Explain your reasoning. So, on number 17, given what the graph has, it has 2 zeros that you see with a degree of 4. Let's just copy and paste the problem. I'll even copy the 17 down. How about that? All right, number 17, it's a degree of 4, but it only crosses the x-axis twice, and the way it crosses the x-axis is linearly. That means these are degrees of 1 where it crosses through. That means this has 2 real zeros of multiplicity 1, and a degree of 4 means it needs 2 imaginary zeros. So, is that all they asked for? Determine number of imaginary zeros. Now, remember, imaginary zeros always have to be an even number, so something went wrong if they're not. 0, 2, 4, 6, whatever. So, 2 imaginary zeros. Function crosses the x-axis only twice, each with multiplicities of 1. Therefore, two solutions by the fundamental theorem of algebra, two solutions remain and are imaginary. I'll put a lowercase o there. FTOA. All right, that's number 17. Number 18, as I feel like copying and pasting again, let's take a look at that one. Degree of 5, interesting. Degree of 5. Did it? Come on, there it goes. If you hear me click those buttons over and over, that's me trying to control V, control V, control V. And it ain't control Ving in those situations. All right, number 18, degree of 5. This has a degree of 5, yet it only passes through the x-axis once right here. Now, it doesn't pass with any sort of multiplicity appearance, meaning if it did this curve through there like that, I'd say, oh, it might have a multiplicity of 3 or 5, I wouldn't tell. That also just has a multiplicity of 1. So there's only one real solution, one multiplicity of 1. That means there are 4 complex solutions, 4 imaginary solutions. So 4 imaginary solutions. Only one real solution with multiplicity of 1. And then fundamental theorem of algebra, blah, 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 5 minus 1 equals 4. So that's the reasoning behind that one. 4 imaginary solutions. Oh, I shudder in fear over finding what those ones are. Now, there are 2 more on this side, 19 and 20. Oh, they are still graphs. So on number 19, we have degree of 2. There's nothing I really need to mark on this one, so I'm just going to write out degree 2. And I want you to just kind of fill in the blank for what we have there. We have a parabola. It doesn't cross the x-axis at all. No real solutions means only solutions can be imaginary. So 2 imaginary solutions, complex conjugate pairs, 0 real solutions because it never crosses x-axis. And then 2 minus 0 is 2, right? So 2 imaginary solutions for number 19. And then I have to pause after this problem. I got to take care of something. Number 20, we got a degree of 3. Now, based off this one, I guess we can copy paste. I could probably draw it on that side, but you know what? I already copied and pasted. So number 20, degree of 3, and it crosses 3 times. You can only have as many as 3 solutions for a degree of 3, and we got them. There are 3 real solutions, so no imaginary solutions. 0 imaginary solutions, all real. Degree of 3, and all 3 solutions, real solutions, are present. Now, they never went full bore with like multiplicity of 2, bouncing off things like that. I think because we couldn't confirm absolutely if something was a bounce off kind of graph, whether that's degree 2 or degree 4 or something like that. So I think it's in their best interest to not do that unless they show us more about the function. All right, let me pause for 1 second here. Okay. All right, and exercises 21 to 28. Write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and the given zeros. So once again, you know, this section feels a lot like the previous section. I mean, they didn't explain fundamental theorem of algebra. They didn't use complex conjugates, things like that. And that's the difference between this block and the block that we had last time with just irrationals. So this will feel very similar. This question could have been asked in the last section. Absolutely. So your factors of this one, I'm going to go straight up into it, right? If these are your zeros, then you have x plus 5 as a factor. You have x minus 1 as a factor. And you have x plus 1 as a factor and x minus 2 as a factor. Distribute only 2 at a time, right? So leave x plus 5 as is. Let's distribute this one. We get x squared minus x minus 2 on that guy. Now, distribute the rest. X is going to distribute in these 3. You get x cubed minus x squared minus 2x. Distribute 5 into these 3. You get 5x squared minus 5x minus 10. And we combine like terms, keep it in standard form, y'all. And we get this guy here. Allegedly. I never check on my solutions, so sorry if it's wrong. Okay. Now, listen, they do say leading coefficient of 1. The rational coefficients, least degree, all that is being taken care of here, right? The difference here, there's no difference in process of problem. The difference now is maybe just your afterthought, looking at this problem in hindsight. Looking at this problem in hindsight now, what did we know? We had 3 solutions. We expected a cubic, right? Number 22, also 3 solutions. We're expecting, once again, a cubic. Not just expecting a cubic, but we write it in least degree in that form. Because there are only 3 factors here, that's what will make it a cubic. So x plus 2 times x minus 1 times x minus 3. It's possible to make it like a quartic if you make one of these a multiplicity of 2. You know, that kind of thing. Anyway, let's go ahead and expand the second 2 guys here. We get x squared minus 4x plus 3. And let's expand the whole. And combine like terms in its finality and totality. Actuality. Minus 2x squared minus 5x plus 6. I look back at these problems and I say, you know, these weren't factorable by grouping, so I don't know. I pity the person who has to bring out those solutions back using rational root theorem. Now 23 and onward, actually not 25, but everything 23 and onward will be new compared to what we had of old, because we have now a complex solution of 4 plus I. If 4 plus I is a solution, that means 4 minus I must be a solution if we need rational and real coefficients. Okay? So rational and therefore real. Now, what they would generally do in this situation is write this out in its factored form, x minus 3. Keep in mind, when you're subtracting 4 plus I from both sides, we can write this, x minus this solution, and x minus this solution. By distributing the negative in those factors, you'll now get x minus 4 minus I and x minus 4 plus I. But the next strategy involved in this to make this cleaner and quicker instead of multiplying a 3 by 3 is to group these x minus 4s as they're the same. Note that this is minus I and plus I here, which is an a minus b times a plus b scenario, which distributes into a difference of 2 squares. A minus b times a plus b is a squared minus b squared. In this case, a squared minus b squared. Now, I squared is negative 1. So when we subtract negative 1, that becomes a plus 1. So this expands here to x squared minus 8x plus 16 minus I squared is minus negative 1, which is plus 1. 16 plus 1 gives us less 17. That's the way the book does it, and it's a totally fine and fair way to do it. I'm going to provide my alternative direction for that thing, which I feel like to me is less steps or less multiple sets of nested parentheses and things like that. So we'll try both together, but we still have to expand and finish this thing off. X cubed minus 8x squared. Now distribute a negative 3. Remember, all the signs changed. Negative 3x squared plus 24x minus 51. And finish. Oh, I think that's a 41x. Hold on. 17 plus 24. 41x minus 51. Okay. How we doing? Number 24. Once again, using a slightly different appearance of method. 2, 5 minus I. Not really difference of method, but just a quicker way to clean this thing up, I believe. If 5 minus I is 1, then 5 plus I is 1, right? If I write these out, you know, if I just wrote out the solution set, x equals 5 plus or minus I, I could get the i's by itself the same way I got radicals by themselves at the time by subtracting 5 from both sides. If I square both sides, I am considering both solutions plus or minus that are there. So in squaring both of these, this becomes x squared minus 10x plus 25 equals, now I squared, positive or negative, I squared is negative 1. And then add the 1 over, you get x squared minus 10x plus 26 equals 0. This, alongside x minus 2 equals 0, because x equals negative 2, let me start with that. This alongside this x minus 2 equals 0 are both of your factors that we're using. We're using this factor and this factor. These are what we have to multiply together. So that's the alternative version of getting into this stage here where we can now write these in factored form together. So it's up to you and what you prefer. I personally prefer this method. I think it's less writing than that as an overall, because now we're at this stage here. I don't know. It's about the same. Depends. X cubed minus 10x squared. Okay, plus 20x minus 52. And lastly, we get minus 12x squared plus 46x minus 52. Okay. Hopefully you're good on me not saying too many things out loud on that. Combining like terms, make sure in standard form, yada yada. Still, so far, nothing looks factorable by grouping. Number 25. Now, on number 25, no imaginaries. We do have an irrational, though, and it must still have a conjugate to in order to have your rational coefficients. So, plus or minus 5 work here. Now, it doesn't matter which way you present this one. I'll do it the way that the book probably would have done it here. X minus 4 with the negative root 5. That would be x plus root 5 inside of here. And the other one would be x minus root 5 inside of here. Now, the bottom line is, guys, this is still a difference of two squares. So at least this one is a lot cleaner and easier to work with. With that in mind, this factors into x squared minus root 5 squared. Root 5 squared is 5. So that was as quick as that. Now we go ahead and FOIL this out. We get x cubed. Now, I'll write it in this form. Outside is minus 5x, inside is negative 4x squared, and last one is 20. But I wouldn't finish here because it's not in standard form. So I have to make sure that negative 4x squared is first, and then negative 5x, and then positive 20. This, by the way, is factorable by grouping, and it would be as such because it's a binomial times a binomial there. I guess that's also the reasons why the others weren't factorable by grouping. All right, number 26. You have nothing but complex solutions here. A couple imaginaries here and there. Keep in mind that given all these, you do have conjugates. Positive 3i, well, negative 3i is also to be considered here. Negative 2 minus i, 2 plus i has to be considered. There are 4 solutions. This needs to be degree 4 at best, at smallest, at least. Now, here's what I'm going to do. I'm going to kind of blend 2 of the methods in one. I'm going to use their method for the x. It's not their method, just the one that the textbook is reinforcing by using the x minus 3i and x plus 3i. Blend it together. We're going to combine it with the other one that's going to come into form with what I did on the other side over here in just a moment. X minus 3i times x plus 3i, difference of two squares, is x squared minus 3i squared. Now, I'm going to write out what that looks like. 3i squared is 9i squared. 9i squared is negative 9. And subtracting a negative 9 gives you plus 9. So x squared plus 9 is that result. Now what comes out of this, if x equals 2 plus or minus I, you can subtract 2 over and square both sides. If you square both sides here, you get x squared minus 4x plus 4. And I squared is negative 1. If I add the 1 inside of there, you can see that that's where I'll get x squared. I'll just bring it down here. X squared minus 4x plus 5. Okay. I squared is negative 1. You add the 1 to this side of the equation, set it equal to 0, all that stuff. So that's where I think that was just, again, a faster version of what I was doing on that. I think I'm going to live with my version the rest of the way if it's not just difference of two squares oriented. So now we can distribute here. We do have a quartic. And then I have plus 9x squared minus 36x plus 45. Oh, yeah. I was going to say, is there anything that combines? Yes, in the middle. So x to the fourth minus 4x cubed plus 14x squared. All right, there we have it. Okay, yeah. 2 more. Number 27. 3. Oh, gosh. There's, yeah, I'm definitely going rogue, guys. Number 27. I have 2, 1 plus I, and 2 minus root 3. Definitely going hard on this. Do I have to write plus or minus 2? No. In fact, you don't want that when it comes to least degree. we're going to do this. But we do need a 1 plus or minus I and 2 plus or minus root 3. Now, when it comes to 1 plus or minus I, we're talking about x equaling 1 plus or minus I. Subtract the 1 over and square both sides because we have the plus or minus considered there. We are considering both. This expands to x squared minus 2x plus 1 equals negative 1, and we add the 1 over like that. On this guy, we have x equals 2 plus or minus root 3. Same thing, isolate the radical. Square both sides. This expands to x squared minus 4x plus 4. And root 3 squared, positive or negative, is a 3. Subtract the 3 over, you get x squared minus 4x plus 1 equals 0. So these are two of your factors, and you still have a third factor, remember, in x minus 2. So now we'll have x minus 2 times this trinomial times this trinomial. So we still have more work to do with this. We're not quite done. Yeah, let's go. So x minus 2 times, all right, x squared. We're going to do this in kind of multi-stage. You know what? Let's do this. Let's do this. Let's use the box method. I think this is quite a bit, so I'd rather box this thing out. Okay. Otherwise, that's 9 terms to write alongside that guy here. So we have x squared, negative 2x and 2, x squared, negative 4x and 1. All right. X to the 4th, negative 4x cubed, x squared. Excuse me. Okay, now the cool thing is here, things that will combine, this stays alone, these will combine, these will combine, these will combine, this stands alone there. So ultimately, what I want to write on this next stage here, f of x equals, I got x minus 2 times, I have x to the 4th, minus 6x cubed, 9x squared, 11x squared, plus 11x squared, minus 10x plus 2. Assuming I didn't make a mistake on signs anywhere, and I very well could have, or I might be ignoring signs. I hope I didn't mess anything up there. That's what we have. And now we still have to keep distributing. I'm not going to use box method again, even though we'll have 10 terms here. We'll have x to the 5th minus 6x to the 4th plus 11x cubed minus 10x squared plus 2. Negative 2 distributes into these. We get negative. I'll just write them vertically. To the 4th plus 12x cubed minus 22x squared plus 20x. Oh, I'm missing. Oh, there should be an x there. Plus 20x minus 4. See, writing it vertically helped me there. All right, x to the 5th minus 8x to the 4th plus 23x cubed minus 32x squared plus 22x minus 4. You know, I feel like solving this one, solving it from here into the set probably would have been faster than what we did through expansion. I just personally feel like, I don't actually know because I didn't actually do the problem there. But, you know, just all told, that was quite a bit. So, what number is that? 27? Okay, so number 27, let's go to number 28. Three, 4 plus 2i, 1 plus root 7. I think this is still going to be quite a bit to take care of. 4 plus. Well, plus or minus will be the case, but I'm going to write it as it originally was. 28, so 3, 4 plus 2i. You can see how habitually I just wanted to write the plus or minus anyway. It's a thing. It's a thing. All right, let's make them different colors this time. Plus or minus, like that. All right, when it comes to this guy, x equals 4 plus minus 2i. I'm going to subtract the 4. As you know, I'm going to be squaring both sides here, right? So squaring this side gives me x squared minus 8x plus 16. I think I got to write this squared. It gives me a good visual confirmation of what was happening. 2i quantity squared is 4i squared, which is negative 4. Remember that I is gone. So x squared minus 8x plus 20 equals 0. There's a factor. On this guy here, we got x equals 1 plus or minus root 7. Or x minus 1 equals plus or minus root 7. Let's square both sides. And we got x squared minus 2x plus 1 equals 7. That's what happens when you square that. Subtracting the 7, you get x squared minus 2x minus 6 equals 0. The other factor is x minus 3. So here we go. F of x equals x minus 3 times this one times this one. And I think the box method served us well last time, so I'm going to go and do it again. This time, let's see if I can draw myself my own box manually. It's a 3x3 grid. Ooh, that's bigger than the others. Good thing I have all that room for that. X squared minus 8x and 20. X squared negative 2x and negative 6. Here we go. You know, it still doesn't feel like much width room. I have all this room to write, and I chose to just fit it in this little box. Plus 16x squared. Oh, I don't really need to write the plus, but 16x squared. And then plus 48x. And then 20x squared, negative 40x, and negative 120. All right, so things still combine down these lists as you kind of saw before. Does this always happen? No, it depends on the degrees of what you have going on. But the way that these degrees go from quadratic to linear to constant, it will work that way. Okay, so f of x equals x minus 3 times, we got x to the fourth, minus 10x cubed, 30, plus 30x squared, plus 8x minus 120. Ooh, hand cramp. Let me pause for a second with my hand. All right, let's keep that space. All right, x to the fifth, 10x to the fourth. These all go up 1 degree when I'm multiplying by x. These all multiply by negative 3, and I'll write it down below the one where it would belong. Okay, now when we combine like terms, we're going to get x to the fifth minus 13x to the fourth plus 60 x cubed minus 82x squared minus 144x plus 360. I know you can't see it. I'm going to bring it over. Here it comes. There it is. Hey. Okay. There we have it. For some reason I locked it in place. Now it can't move. It's stuck like that forevermore. All right, so those were some problems. I don't even know what to say about it. Those are some problems. Okay, let's go to numbers 29 and 30, error analysis. Describe and correct the error in writing a polynomial function with rational coefficients in the given zeros. Well, they didn't use my method. That's the problem. All right, on number 29, they have 2 and they have 1 plus I. Now, as they're working some things out here, they wrote the x minus 1 plus I, and they have it going on, and they start their distribution process. The problem is, as you can see, they still have imaginaries within their coefficients. Their x term is 3 plus I. Their constant term is 2 plus 2i when it comes to imaginary numbers. They don't have rational coefficients in this thing because they didn't induce its conjugate. Nothing they multiplied is incorrect. They correctly multiplied. They need the minus I here, 1 plus or minus I. So they did not include 1 plus the complex conjugate, the conjugate for the complex number, 1 plus I into its solution set. And they were left with some imaginary non-real coefficients. Irrational. Not just irrational, but non-real. Like that's really the whole goal there. So our zeros we actually want to have in this case, and I should have been writing the word out zeros whenever I wrote my list before, but our zeros are 2 and 1 plus I and 1 minus I. So that's needed. So we're still doing the same stuff as we were doing on the last problems. It looks like we got to do it for both sets here. So we are going to have, let's see, I'll do their form this time. So x minus 2, because I want to keep it consistent with what they showed you. They showed you x minus 1 plus I, but now they got to show you also x minus 1 minus I. So Here, distribute the negative, x minus 1 minus I, and here, x minus 1 plus I. And let's group up this time x minus 1s, treat it like our a, and I like your b for a squared minus b, or for a minus b times a plus b. So it distributes into become a squared minus b squared. Now let's see if we can kind of do this in one step. A squared is x minus 1 quantity squared. Minus b squared, we're going to subtract I squared, which is subtracting negative 1. That means we're doing plus 1. That's what that turns into there. That's where we can kind of save ourselves a little bit. X minus 1 quantity squared is x squared minus 2x plus 1. And we got a plus 1. Why don't we just put plus 2? Sound good? Now we can go ahead and distribute all this out. We get x cubed minus 2x squared plus 2x minus 2x squared plus 4x minus 4. Negative 2x squared minus 2x squared is here. 2x plus 4x is here. And negative 4 is there. And that has rational coefficients. That's what we were looking for. Not that I stuff. We don't want the I stuff. Number 30 seems to have the same issue somewhere because they still have I stuff. As you can tell, they have x squared minus 4i minus 3. Where did they go wrong? Let's find out. They wrote, okay, the issue was they did this here, x minus and x plus, and kept the same solution. They're not supposed to change the signs inside the factoring. It's not negative 2 minus I, as in like the whole thing. So it's not x equals 2 plus I and x equals negative 2 plus I, because that's what would bring about what they had here. What they did. This is what they did. What they should do is x equals 2 minus I. What they should do. I know it's kind of strange, but anyway, so it changes what you have in that sense, and because they, had their system written out, I want to do it the same way. So x minus 2 plus I times not x plus 2 plus I, but x minus 2 minus I, which will change the result. I want you to see the difference here. The difference also will be, of course, that we get all rational coefficients. So this will become x minus 2 minus I, and this will become x minus 2 plus I, and you can see that difference now in what we have. This actually wouldn't have given us any difference of 2 squares work. That's why they had to do all this time. Here, we do get to do some difference of 2 squares work. We got x minus 2 in both of these as our a. Minus I and plus I is your minus b plus b. And this becomes a squared minus b squared. If you've noticed each time here, though, what happens is x minus 2 squared. This becomes, once again, plus 1, because this is minus I squared, and I squared is negative 1. So we are going to add 1 to this result, where this becomes, actually, we don't even need a second set of parentheses. This is it. We're set. So we're just here. This is x squared minus 4x plus 4 plus 1, which is x squared minus 4x plus 5. Okay. All right, that is number 30. And that's the bottom of the page. Water hit. Okay, number 31, open-ended. Write a polynomial function of degree 6 with zeros 1, 2, and negative I. Justify your answer. All right, the zeros that I do have are 1, degree is 6. Degree is 6. Zeros are 1, 2, and negative I. Now, a required thing we'll need is a positive I, right? That leaves us with a degree of 4. If we want to get a degree of 6, and these are the only zeros we can kind of have, if so, maybe we can do something like give this one a multiplicity of 2 and this a multiplicity of 2. That's an option. We could give this a multiplicity of 3 and a multiplicity of 1. It's kind of your choice thing when you do that at that time. Let's do a multiplicity of, we haven't seen multiplicity of 3 in a while. I'm going to go ahead and bring that about, and I'll do it with the 2. I'm going to make this number bigger. Multiplicity of 3 and multiplicity of 1. Does that give you 6? That's 1, 2, 3, 4, 5, 6. Yes. So when written out in factored form, guys, this will look like x minus 1 times x minus 2 cubed times x minus I and x plus I. Okay. X minus 1 is exactly that. X minus 2 cubed. Now this turns into x cubed minus 3 times x squared times 2 plus 3 times x times 2 squared, 4, minus 2 cubed, which is 8, minus 8. And this multiplies by x minus I times x plus I is x squared plus 1, because it's x squared minus I squared, or x squared minus negative 1, x squared plus 1. So let's get this down on fitting on one line again. X minus 1 times, I'll put the x squared plus 1 here, x squared plus 1 times x cubed minus 6x squared plus 12x minus 8. Okay, distribute 2 at a time. Let's go with these guys first, the two binomials. This leaves you with x, I'm going to write it in standard form right now, x cubed minus x squared plus x minus 1 when you multiply things out that way. And this is x cubed minus 6x squared plus 12x minus 8. I really feel like the box method is in order here. I think it's going to be, otherwise it's going to be a 16-term thing. This was my choice for making it that way. Now, things will combine eventually, right? But given that it's going to be 16 terms, I think there's just a lot that I want to fit in here. So let's make it as organized as possible. Cleanliness is your friendliness. Not equally spaced, but I can fix this. Looks a little bit better. Okay. All right. So let's go. X cubed, negative x squared, x and negative. The only problem with the box stuff for me is like I spent so much time making the box. I could probably like be done otherwise. X cubed, negative 6x squared, 12x and negative 8. Okay. So here we go. 6. Just be very careful with everything that you're doing. I don't know if I am being careful. I do this kind of faster than my own, or, you know, too fast for my own good. Especially if I talk during it. Maybe I should hush hush. I think you'd be very thankful if I did hush hush. Okay, once again, what I really like about this one, or at least my setup of it, is that these things are going to combine down these diagonals here. X to the fifths, x to the fourths, x cubeds, x squareds, and x's. So it's a nice part about this cleanliness here. 16 different terms. These don't combine with anything, but they are what they are. Okay, so from there, let's see if we can write this in one step and be done. My open-ended answer to this question is f of x equals x to the sixth minus 7x to the fifth plus 19x to the fourth. It's negative 20, negative 27. Negative 27x cubed. 26 plus 26x squared minus 20x plus 8. Where's my 8? Where's my 8? Oh, these are two different things. Okay, 7 terms in this, and yet I'm sure that's right. And that's when I think that I was probably faster doing this than using rational root theorem, all depending on what would have happened. All right, that was an open-ended one. Number 32 on reasoning. 2 zeros of f of x equals this are 4 and negative 4. Explain why the third zero also must be a real number. So I don't think they're asking us to solve this. Sorry, it's 36 or 32. I don't think they're asking us to solve this thing, but what they are kind of letting us know is information. X equals 4 and negative 4 and now this solution, here's what I'm going to type out. This solution must be a real number. I don't know what it is. We could find out. I don't think I'm going to. This solution must be a real number because if it was an imaginary number, it would require to have a complex conjugate pair since the original polynomial has all rational coefficients. It cannot have one, though, because only 3 solutions are allowed in a cubic function, according to the Fundamental Theorem of Algebra, right? We can only have 3 total solutions there. So that would be the reason. Honestly, if I were to solve that, I'd probably use long division on this with x squared minus 16, given how those things would multiply out, stuff like that. I'm going to leave it. I think we can take our word for it for now. If you ever need me to go back for a problem like that, we can. All right, next it says 33 to 40. Determine the possible numbers of positive zeros, negative zeros, and imaginary zeros for the function. This is where we're using Descartes. Was it rule? I forget if it was rule or theorem. Descartes' law, Descartes' principle, Descartes' method, Descartes' process, whatever it was that we're doing. We're not solving these. We're coming up with the stuff. Now, what I remember is they kind of did a table. What I'm going to do, let me pause this and let me bring a table template in these, because I think it's going to have to be used each time. Give me a second. Okay, so here's what I decided to do. Because I have to change the number of rows and columns and stuff, and I can do this and like delete some, I can like, oh, I forgot how I just did that. I can delete these cells and things like that. I made my own version of one that I can use off of these. Okay, so here's the idea. Descartes' theorem. Oh, and I should have looked up what the name was. Descartes' thing. Actually, let me see what it's called. I have another PDF that has the thing up. Descartes' rule. Okay, Descartes' rule states that that number of sign changes based off the positive version of this and the negative version of this tells me how many positive, negative real zeros we can possibly have. Now, this is x to the 4th minus x squared minus 6. It's in standard form. Remember, this is positive to begin with. So there's one sign change, and there's only one sign change. Now, because of that, the possibility of positive real zeros is 1. You can't have 0. You can only have 1 in that scenario. Now, g of negative x is something else that we have to also test on, and that would be negative x to the 4th minus negative x squared minus 6, which becomes x to the 4th minus x squared minus 6. There's no change in what happens because squaring a negative turns those positive, right? That's the idea. So once again, just one sign change. So the only possibilities here when it came to positive real zeros and negative real zeros, there can be one positive real zero, and if that's the case, if there's one positive real zero, there can only at most be one negative real zero as well, which means there will be 2 imaginary zeros and then 4 total zeros. There's no chance that we can have 3 negative real zeros, as you can tell, right? It's only combinations of their maxes and stuff like that. So really, this is the only option when it comes to answer. There's nothing else that's provided for that. So it's just a table where you just have 1, 1, and 2, like that. So that means I can delete all these other ones. I mean, I might have to reconsider that when it comes to copying and pasting this later, but delete these cells here, and that's the only possible outcome for this. So there's 1 positive, 1 negative, 2 imaginary, etc. Okay, so there's the 1. I have to find a way to copy and paste this now and not bring those other ones in the fold because they are going to come into the fold. Let's see. I can just erase those. Yeah, this is really a table-based version. I guess I'll leave it like that and we'll expand as we go, right? I'll keep this on hand on the side. Give me one on the side. There we go. All right, let's go to number 34. Sorry, I have a lot of window things to take care of with these tables now. Number 34. All right, in number 34, we have g of x equals negative x cubed plus 5x squared plus 12. Now, remember that this needs to stay in standard form. It's okay if coefficients are skipped along the way. I don't know if I may mention that enough. Like this one went from to the 4th power to 2nd power to constant, so we skipped the cubic and the linear. But in between would have been zeros. We neither add nor subtract 0, or we have no way of differentiating. So just keep that in mind when it comes to this. Now, this starts negative and it turns positive, and that's it. So there's only one turn. That means at best you can only have one positive. So as far as positive real zeros, it's just that. When it comes to negative, we got to take a look at what happens when we do g of negative x. Now, g of negative x would get opposite of negative x cubed plus 5 times negative x squared plus 12. Cubing a negative keeps it negative, and the opposite of that's positive. So you get positive x cubed. Negative squared is positive, so that's plus 5x squared and plus 12. There are no terms on this thing. It's positive, positive, positive. So there are no possible negative real zeros. So when it comes to the table, this is the only option once more, just one row. 1 plus 0. And plus something needs to be 3, right? Because this needs to be a cubic. So in order to be cubic, the only possibility is 2 imaginary zeros. And that must be the case. As far as possibility goes, that's the only one that you can actually possibly have. So it's 1, 0, 2, and 3. All right, number 35. I'll paste the table after now that I have it. So number 35, we have x. I hear my phone going off again. G of x equals x cubed minus 4x squared plus 8x plus 7. When it comes to our g of x, there are 2 sign changes. We go from positive to negative and negative to positive. That's 2 of them. Let's look at g of negative x after. So anytime I draw an arrow, consider that to be a tally, if you will. G of negative x is going to be negative x cubed minus 4x squared minus 8x plus 7. I'm skipping a few steps there, but keep in mind, anytime you raise to a negative power, the sign will change. Anytime you raise to a positive power, the sign will stay the same. I guess that's basically the instance that we're talking. I said a negative power to an odd power. Let me say that again. You raise to an odd power with a negative, sign will change. You raise to an even power, the sign will stay the same. 7 is just a constant. There's nothing to plug in there. This one only changes signs once right there. So given that the positive one is 2, your options are 2 or 0. Remember that. Your options are 2 or, whoopsie. Oh no, what happened? Your options are 2 or 0. Oh, my whole thing got kaput. Let me do that one more time. I'm sorry. Whenever this thing pastes, some things get in the mix. That's digital art for you. So I need to at least consider a second row. I need to at least consider a second row where if the positive, I think we'll have to consider more than this. Let's see. If the positive was 2, given that it's a cubic, the negative has to be 1. Negative can't be 0. So negative has to be 1, in which case there are 0 imaginaries, and that's a total of 3 zeros. That's what we expect. Now there can be 0 positive real zeros. With 1 negative real 0, that means the other 2 would have to be imaginary, and that still adds to 3 there. So that's the combination of those 2 that we would have in that set. Number 36. G of x equals x to the 5th minus 2x cubed minus x squared plus 6. Let's write g of negative x now to get the feel. Raise that to an odd, that's negative. Raise it to an odd, that will change sign. Raise that to an even, the sign will stay the same, and this sign will stay the same. So as far as g of positive x, there's 1 sign change here and 1 sign change there. That gives you 2 or 0 possible positive solutions, real solutions. This is a 1 sign change, 2 sign changes, 3 sign changes. That gives you a possibility of 3 or 1. Maybe I should write those. 2 or 0 for positive, 3 or 1 for negative. So we have to consider all possibilities for there. Our numbers have to add to 5. Our numbers have to add to 5. So I need to insert a few rows. I believe at least 4. Let's see how that works. So, because I'm not extremely savvy in terms of predicting that. I need at least 4, I believe, though. So one scenario is if you have 2 positive, you can also have 3 negative. Given that they already add to 5, you don't need any imaginary. You can have 2 positive and 1 negative. Therefore, you would need 2 imaginary to add to 5. You could have 0 positive in these other cases. If you have 3 negative, that means 2 imaginary still. And if you just had 1 negative, that leaves 4 imaginary. Remember, the imaginaries need to come in conjugate pairs. They also obviously need to add to 5 in this case. So that's an expected answer set for that. Okay, sorry, number 37. Number 37, we have, in the original, a few sign changes. And let's get the negative 1 out right now. Oh my gosh. Let me just erase that instead of undo. I hate when it registers so much for things to undo there. G of negative x equals, this is negative. This will change sign as well. This will change sign as well. This sign will stay the same. So let's look at the positives. We go from positive to negative, negative to positive, positive to negative. That gives us 3 or 1. This is negative to positive, positive to negative, and that sign stays the same. So this is 2 or 0. Remember, they go down by 2's. So I think that gives us another table of 4 to deal with, right? So we have to increase this to 4. There's no faster way to do this. I tried. Okay, so the combinations for us, let's just write them out. There's either 3 with 2 or 3 with 0 or 1 with 2 or 1 with 0. They have to add to 5. So 3 plus 2 is already 5, so give you 0 there. 3 plus 0 plus 2 is 5. 1 plus 2 plus 2 is 5. And 1 plus 0 plus 4 is 5. I think it's a lot of the same like we just had in the last problem. Was the last problem like that? Oh, close. Slight alteration from the last problem, but still the same idea of numbers. Okay, number 38. Bigger polynomial, probably a lot more sign changes, which means I probably have to get my table thing ready for many more than just 4 rows. All right, let's start with this one just to see what's going on. Positive, positive, negative, negative, positive, negative. Okay, that's a case of 3 or 1 for positives. For g of negative x, hopefully you're good on this sign change idea. This change, same, change, same, change, same. How many sign changes? 1, 2. 2 or 0. Okay, that looks like another 4. What I'm actually going to do is copy this one here and paste. Actually, this might be the same. This might be the same as the previous answer. So let's see. Oh, that didn't copy. Come on now. Let's try that again. Come on now. Come on now. Copy. Register that copy, please. Paste. There we go. Wouldn't this be the same answer? 3 positive or 2, which is 0. 3 or 0. 1 or 2. 1 or 0. I don't see how that's any different. It seems to be the exact same as before. So yeah, this is going to be the exact same as before. Good thing the copy and paste was perfectly set up for that one. Number 39. Whoa. 6 degrees, 7 terms. How many changes are we going to have here? G of x is... Actually, not many for the positives, at least. We'll see on the negatives. Positives, there's 1, 2, 3 sign changes. So 3 or 1 are possible for the positives. Les negatives. Sign stays the same. Sign changes. Sign stays the same. Sign changes. Again, we're raising to odd powers there. Sign stays the same. Sign changes. Sign stays the same. So from positive to negative is 1. Negative to positive is 2. Positive to negative is 3. So it will be slightly different, 3 or 1. But it still is only 4 different possibilities of things. So if I paste this old one from before, all we have to do is change the negative zeros, and which in turn changes the imaginaries, of course. But now remember, this is degree 6. Oh, and total zeros, because this is degree 6, right? So being degree 6, you can have 3 negative zeros, which means 0 imaginary, which adds to 6. These got to add 6, right? So 3 plus now 1, which leaves you 2 imaginaries. Or we can have 3 negative with 2 imaginaries. Or 1, now I need to make all my ones look like this. Or 1 negative with 4 imaginaries in that set. So another row of 4. Moving on. Okay, number 40, last one of this set. G of x. At least it's less terms. X to the 7th plus 4x to the 4th minus 10x plus 25. Now we still need 7 solutions, right? So when it comes to sign changes here, positive, positive, negative, positive, that's a 2 or 0 case for positives. For negatives on g of x, we get a sign change on this negative. Positive, keep that sign the same. Sorry, not positive. Odd degree, even degree. I'm calling odd degrees negative, and I'm calling even degrees positive. I shouldn't be saying that. Odd degree, change the sign. Even degree, keep the sign. Okay. So for this one, we go from negative to positive. That's just 1. Just 1 in that case. So this is only going to have 2 different rows. I'm still going to paste that old one because that's what's in my copied set. Let's bring that down just a little bit. And let's delete some rows here. Oh, I guess I can't delete rows unless I delete some of these numbers. Let's get rid of the numbers first. Let's try that again. Oh, delete cells. There we go. Okay. So let's just get rid of these anyway. All right. So they have to add to 7. Let's put the 7s here to begin with. I think that's an easier way to go about it. You'd either do 2 or 0 positive, so you have to have 1 negative. 2 plus 1 is 3. 3 plus 4 is 7. 0 plus 1 is 1. 1 plus 6 is 7. Those seem to be your only options for that set. Okay. Number 41. Which is not a possible classification of zeros for f of x equals x to the 5th minus 4x cubed plus 6x squared plus 2x minus 6. Explain. Let's write it out and see what we can indicate for ourselves. Which is not a possible one, so which one's false means the other ones are true, I suppose, right? All right, let's see what they're saying. 3 positive real zeros, 2 negative, and 0 imaginary, da, 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 da. I think it's easier for us to just come up with our list and go off of that, right? So negative or plus, change sign, keep the sign the same, change the sign, keep the sign the same. Okay, so to us, what are we looking for? Sign change 1, 2, 3. So we have 3 or 1 for positive, and sign change 1, 2. So 2 or 0 for negative. I say we just make a table, and then we come up with, ruling out. Oh, sorry. And we come up with ruling out what shouldn't be. Oh no, this is happening again. Hold on. This is really hard to paste in and drag over. I have no idea why, but it's harder than it looks. Technology, right? 3 or 1, 2 or 0. Okay, this is the perfect table set that we need, and it's a 5th power thing. So this is perfect. This is just a copy and paste of like number 38 or something like that. I forget which one, but perfect. Okay, which ones do work, which ones don't? Let's look at A. 3 positive, 2 negative, 0 imaginaries is good. So if that's good, then that's not the right answer. Because they said what's not possible. 3 positive, 0 negative, 2 imaginary. That one's good, so that's not the right answer. 1 positive, 4 negative. 4 negative's not possible, so this will be the answer. The most we can have is 2 negative, like this. 1 positive, 2 negative, 2 imaginary. So the answer here is C for number 41. That's how I'm going to write it with this in mind on the problem itself. Okay, number 42. Using structure. Use Descartes' Rule of Signs to determine... Descartes' Rule of Signs. That's the full name. Descartes' Rule of Signs to determine which function has at least 1 positive real zero. Let's just look at the lists and make a determination off of that. This one has at least 1. This might be multiple selection. I don't know. But this has 1 sign change, 2 sign changes. So this one works. These are the original f of x's, by the way. This doesn't have any sign changes, so that does not work. No sign changes. Okay, it's just A. It was just multiple choice. I'm just answering it right there. I hope that's okay. But 2 sign changes on that one. I'm just going to put A. Quickest problem in the book. Number 43. Modeling with mathematics. From 1890 to 2000, the American Indian, Eskimo, and Aleut population P in thousands, maybe Aleut, I don't know, can be modeled by this function. Looks like a calculator usage possibly. Where T is the number of years since 1890. In which year did the population first reach 722,000? Okay, so P equals 0.004 T cubed. Okay, they said which year did the population reach for 722,000? Remember, P is already in thousands. So if we set our population equal to 722,000, or if you write it as 722, then you get this setup right here. Now I'm going to be subtracting 722 from both sides, combine it with the 243, and then we'll have ourselves a function which we can model set equal to 0 and use the graphing calculator to come up with what we need to come up with. 722, so 243, let me go to the calculator now. 243 minus 722, negative 479. Okay, I am going to write an equation y equals this, and we want to find out where it crosses the x-axis. We want our time to be a positive number, 0 or positive. It needs to be somewhere between 0 and 110, because those are the years from the years 1890 to 2000. So let's go to our calculator, and we are going to do 0.004x cubed minus 0.24x squared plus 4.9x minus 479. Now, what we're going to do here, listen, based on Descartes' Rule of Signs, I don't know if this part really matters or not, but based on Descartes' Rule of Signs, there are 1, 2, 3 different sign changes. That means we have 3 or 1 different times where the population will become this that are positive. So the 3, there are the possible 3 that there are. Maybe the other ones are outside of from 0 to 110. That's very possible. So I'm honestly just going to look in the window range from 0 to 110. There may be more than one answer. But it says in which 1 year. So I'm guessing we're just going to have 1 year that's there. So let's go from 0 to 110. And I guess the y window range there is fine. Listen, this thing's going to spike up and down so much. Or fine, I'll give you the whole graph of this. Let's go from like negative 1,000 to 1,000. Just make sure it hits everything. If this curve is too small, I'm going to omit it and change it. That curve actually looks perfect for what we need. So this cubic was doing something else along the way. I don't know what, but we want to recognize what that individual 0 is right here. And I can't just go over it and say, oh, it's about this. I'd rather do a little bit more on that. So I'm going to, it's around 67 something. Let's just zoom in on it. Let's zoom in on it a little bit just to make sure that it makes more sense than what we're looking at there. So around that. Now there's a trace feature on your calculator. It's around 67 something. There's a calc feature above this trace button where we can find a 0. They say choose something to the left of your thing and to the right of it. Make sure that you're pinpointing which one it is. And it's going to be this number right here, 67.92, etc. So t, in our case, when the 3 or 1 was possible, it looks like 1 was it. And that t equals, for our purposes, 67.921741. Now, what does this matter for us? This is number of years since 1890. Now, they said, in which year did the population first reach 722,000? When you do 1890 plus 67.9-ish, whatever, you get 1997, I think. Well, 1957.9, whatever. That means it was in the year 1957, right? You don't round up to 1958. It didn't yet reach 1958. We're still in this other year. So the year, in this case, is 1957 in which that happened, because it's that many years after the fact that occurred. Okay, so that's what we're doing on that thing. Or at least that's what I believe, right? It was a number of years since then. Did it reach 720? Can we not round up, right? We can't round up? If in 1890 is year 0, okay, I'm going to say 1957. I believe you cut off. I'm trying to make sure that it's not a rounding up effect. So I'm going to go with that. That's my belief. Okay, number 44. Modeling with mathematics. Over a period of 14 years, the number n of inland lakes infested with zebra mussels in a certain state can be modeled by this big guy. All right. A lot of stuff. Hold on. I even need to write this on multiple lines. How about I just copy and paste what's written there, because I won't be able to fit this on one line cleanly, but I will probably have to do more of my own work after this. Just first time through will be helpful for me. A little bit less writing didn't hurt nobody, right? Definitely didn't hurt me. Okay, so there's the initial. Now, in which year... over a period of 14 years. In which year did the number of infested inland lakes first reach 120? So the number n of inland lakes. So t is the year. We need 120 to equal this. So let's subtract 120 from there, basically. And that'll be negative 122.5. Sorry, I'm still saving myself some work in writing. So that'll be now negative 122.5 and set this equal to 0, right? That's basically the understanding that we have on these ones here. Let me do some little alterations with this. All this work to do just to save myself a couple lines of writing, even though I've done so much writing before. But I think that's the point. That's why I've done so much writing before. I want to address what's going on there. There we go. Looks a little better. All right, so setting that equal to 0, we're now going to solve for this one. And the same kind of thing. When it comes to sign changes, there are 1, 2, 3, 4 of them. That means we're either going to see 4 or 2 or 0 positive answers. We need to only go from t between 0 and 14. They said the first over a period of 14 years. So we're only going to look for one between 0 to 14 in this set. We're going to do that in the calculator in the same way as we did before. So we now have this. Now I got to type all this. 284 t to the 4th power. It's overriding everything else, and this one's longer, so I think we're going to get past all that. 5937 cubed. Okay, I'm going to have to edit something out. In the midst of my recording, there was a very scary, loud door knock on my door. It was just bang, bang, bang. I'm like, oh my God. I wanted to go there and say, I got a gun. But what I also noticed when coming back here, guys, is I have a couple zeros there. I want to address that one and make it just 1 0 like that. Okay, when it comes to window range here, we want to go from 0 to 14 on this, though. Okay, because the range is from 0 to, the domain is from 0 to 14 on this. And we're going to find where it hits at least once on this thing, right? If it hits again, well, it hits again. And it doesn't. It almost does hit again, right? Because the idea is it's going to hit 4 or 2 or 0 times on positive t values. We only care about the one from 0 to 14. So we only care about this one right here. Now, what is that value? We can go and hit calc and find the 0 with the left bound here. Sure, let's hit something to the right of this number. Let's figure out what that is. Let's go to the right, to the right, to the right. Okay, there's something to the right of it. And it's going to find this value for us at 9.025. So about 9 years. 9 years into this thing, we'll be all set. Okay, number 45. Also modeling with mathematics. For the 12 years that a grocery store has been open, its annual revenue R, in millions of dollars, remember millions, can be modeled by the function R equals yada, yada, yada. Now, they have a 0.0001. I got to be careful because I made a mistake last time. But 0.0001 distributing into all of that. Do we want to write it distributed or not? It's up to us. Here's the thing. When it's in millions of dollars, why don't we just multiply everything by a million? It's up to us. Anyway, so 0.0001 times this guy. Oh, should I just copy and paste it like last time? Totally, right? So in where t is the number of years since the store opened, in which year or years, they say year or years, was the revenue $1.5 million. So it's possible there's more than one solution. Now, by Descartes' Rule of Signs, if that's the name of it, is it also possible? See, 0.000 whatever 1 doesn't change, sign changes, and from here in standard form, there's 1, 2, 3 sign changes, so we can have 3 or 1 possible solutions here. Now, we're going to be looking for the 12 years of time, so within this time frame, it may hit once, it may hit twice, in this time frame. You have to remember, it hits 3 total positives, possibly, but the 2 may only be in this domain. So we'll see. I have no idea. So I got to type this whole thing in. We have to do some changes, though, right? What do we have to do? Set this equal to 0. Well, set this equal to 1.5. Remember, this is already represented in millions. Set this equal to 1.5. We got to subtract 1.5 over, but this is where you got to kind of be careful, because the 0.0001 would technically be distributed into this. When you multiply that, then you could subtract 1.5. So let me show you what I'm saying. Let's take this. Listen, we could do distribution right now if we wanted to, but we're just going to multiply this by 0.0001. I want to make sure that my decimal thing's appropriate here. So 0.0001 times 13650. And that number is 1.365. Okay. Now, if I subtract, because I'm going to subtract 1.5 to both sides, the minus 1.5 would make this number negative 0.135, like that. If I divide this, if I factor out a 0.0001 from there, again, then I'll get the true number that goes inside here afterward. So divided by 0.0001, I'm now getting negative 1350. So instead of getting this number here, let's write this as negative 1350, given that we're going to set this equal to 0 instead of having that r. So this is the model we're going to be using. Remember, this is still in parentheses. This is the model we're going to be using, assuming we never distributed that 0.0001. And now we work off of that. So a little bit tricky as far as their setup goes. I guess that's what they wanted to do with you on it. So let's go ahead and try that out. So 0.0001 times negative x to the fourth plus 12x cubed minus 77x squared plus 600x minus 1350. And that's all in parentheses inside the 0.0001. My window wants to go from 0 to 12. I still have a random y window range, whatever, that's okay. And let's see how many times this quartic crosses through here on the positive side. Well, it didn't at all. Let's make sure I didn't make a mistake then. So, yeah, I totally expected something there. Maybe it just doesn't at all for this actual time frame. Make sure I wrote all that stuff right. Minus 1350 inside of there. So maybe it just doesn't at all, right? It's possible. I don't expect that. So let's see where I maybe made a mistake on this one, right? I don't actually know. Let me zoom out on this a little bit and see what's going on, and then I'll go ahead and make fixes if I need to. Negative 20 to 20. There's the curve. Oh, you know what? My thing is probably just too small on y. They're probably there, we just don't see them. So let's go from 0 to 12 again. Let's totally shrink y significantly more. Let's just go from negative 10 to 10. Probably way too extreme for what we're doing. I was like, what's going on? Oh, there's part of the curve. So my y really needs to shrink, guys. We're talking, remember, y is in millions, so we're not going to see upwards to 10 million. There's my curve. Okay. So it's all about window range. I was like, where is my graph? So it's right there and there. I'm going to shrink it even more, man. I'm going to go way down. Negative 0.2 to 0.2. We're really talking small bits of revenue in comparison. There's my curve. I'm like, I didn't do anything wrong. This looks great. All right. Awesome. So there are my two values. Now, we have to, listen, they're being very ballpark about their values, so I'm not going to hit exact numbers. I'm going to see it's about year 3 and year 9. So year 3 and year 9 are them. Now keep in mind when we talk about these things, how do they ask it? In which years? Yeah, years 3 and 9 is what I'm going to say. If they said since the year 2000 or whatever, we'd say 2003 and 2009. But years 3 and 9 are where they happen. This time I'm not worried about rounding and stuff like that. I feel like they just want to get to the nearest one, and I think that's fine as far as when we do that. All right, so sorry for some hitches in my performance. Every so often I'm looking at the corner of my screen. I get notifications and some things. I thought it was a text. It was actually a YouTube comment from, like my math channel, whatever. And I like to respond to those immediately. Otherwise, I ignore the notification and then I don't see it later. So I paused. I wanted to answer the question. Now I'm moving forward. If I get more, because sometimes I have conversations with this person as they ask questions, I'll maybe pause again. I know it means nothing to you, but when it gets a little hitchy, that might be something for you to go like, stop it. I need consistent flow. Okay. Number 46, making an argument. Your friend claims that 2 minus I is a complex zero of the polynomial function f of x equals x cubed minus 2x squared plus 2x plus 5i, but that its conjugate is not a zero. You claim that both 2 minus I and its conjugate must be zeros by the complex conjugates theorem. Who's correct? Justify your answer. Well, hold on a second. Why are they putting words in my mouth? Why am I making a claim about a conjugate here? I don't want it. No. They how dare they do that? I didn't make such a claim. Stop it. Stop it. Okay. So here's the thing. Now, I don't know whether or not 2 minus I is a zero. I'm going to assume that it is. We can do some synthetic division and figure out whether it is or not. But it says that I claim that both 2 minus I and its conjugate must be zeros by the complex conjugates theorem. I'm not correct in this case, or at least unless there are other imaginary solutions, I have no grounds to stand correctness. I have no reason to guarantee that I'm correct. Sorry, there is no reason. There's no reason to guarantee that I'm correct. See, we've talked about complex conjugates. The difference is those were used to give you rational, real coefficients. I have an imaginary coefficient of 5i there. 5i is one of the is the constant term in our polynomial, which means not all coefficients are rational. So it stands to reason that there may not be complex conjugate pairs in this problem. Now it says who is correct. I guess if 2 minus I is one of the zeros, then my friend is correct. If, therefore, it appears my friend is correct. It's kind of a weird question. Because it could be something like, this person's eating chocolate cake. This person's eating whatever cookie. Who is eating healthily? Like, well, maybe no one is, right? I don't know that my friend's correct, but they could be. We could do more to figure out whether or not that's true for the 2 minus I. Like I said, you could use synthetic division on it. It's a little tricky to use. I'm kind of willing to give this one a shot. If I use 2 minus I here, this might be the first and last time that you'll ever see this. I don't know. Maybe they're going to give you another problem with it later. But if they give you this, we need to see if we get a remainder of 0 out of this. So you put in 1, you multiply by 2 minus I, and then you combine these, you get negative I, multiply that by 2 minus I, and you get negative I times negative I is positive I squared, which is negative 1. And then you get this 2 times negative I is minus 2I. 2 plus negative 1, of course, is 1, so 1 minus 2I. And then you have to just FOIL this. So you get 2 minus 4i minus 1i is minus 5i times positive 2i squared, which is negative 2, and 2 minus 2 is 0, so you get negative 5i. 5i minus 5i is 0. Yes. So you get a 0 remainder here. Now, I'm not going to write what remains here. That doesn't matter. The important thing is because you get 0, that means this indeed is one of your zeros of your function. So your friend is correct. Therefore, based on synthetic division below, my friend's correct. And listen, it's possible that I'm correct as well. I could still have that thing. Well, actually, no, I couldn't. Yes, I could. It's possible. I'm not going to try it. It's possible I could be correct. We could have complex conjugate pairs, and we could have another imaginary number that all multiplies to become this. But it's unlikely. So it looks like that's just their setup of the question. It's asked a little strangely, but it still works. All right, number 47, mathematical connections. A solid monument with the dimensions shown to be built using 1,000 cubic feet of marble. What is the value of x? Okay, x is that height and also the prism's height there as well. So there's a lot to break up here. I think what we can just do is take the volume of the bottom plus the volume of the top pretty easily. What we have to do, though, is find the dimensions of our pyramid up top. So the bottom has 2 3s right here and then a 2x. So this base edge is 2x plus 6. Oh, I guess that means this is 2x. And this is also 2x plus 6. And this is also 2x there. Okay, perfect. So what we have here are volume of object, I'm going to call this object 1 and object 2. Volume of object 1 is area of base times height. Now the height is x, so I'm going to write it like that. So this will become, okay, this is 4x squared plus 24x plus 36 before multiplied by x. That's expanding this thing here. If you multiply by x, this becomes cubed and squared and an x right there. So this is the volume of object 1. The volume of object 2 is 1/3 area of base, which is 2x times 2x, that's 4x squared, times height, which is x, so that becomes 4x cubed. So 1/3 4x cubed, or 4/3 x cubed. Okay, that's how pyramids work. So we add those together, and we can set it equal to 1,000. Now, I'd love to multiply everything by 3 ultimately, because I don't like my uncommon denominator. So let's do, let's just write volume of total equals, I'll just write it as total first. 4 could also be 12 thirds. So 12 thirds plus 4 thirds is 16 thirds. So 16 thirds x cubed plus 24x squared plus 36x. And add that all together, this will equal 1,000 cubic feet. If we multiply this all by 3, that should help us out, get rid of the fraction. 16x cubed plus 72x squared plus 108. X equals 3,000. All right, moving forward, we want to set this thing equal to 0. I want to clean this thing up first. Let's divide it by 4. So we'll get 4x cubed plus 18x squared plus 27x. Let's subtract that over. Divide by 4 is 750. Subtract it over, you get minus 750 equals 0. Now, it's not factoring by grouping. I wonder if they want to use graphing calculator or rational root theorem or something like that. I think at this stage, because the numbers are so big, might as well go to graphing calculator. I mean, I can use rational root theorem within there as well, but if we do 4x cubed plus 18x squared plus 27x minus 750, whoops, minus 750, we would get, there we go. So it seems to cross at 4. Well, that's not 4. That's really close to 4. But it seems to cross really, unless that's, I can't tell if that's 4 or not. Doesn't look like it. Let's see. Let's find the 0. Left of that number, right of 5. Or left of 5. Right of that number. 4.25777086. I forgot, like, you know, this, I don't know if that's rational or not. 4.2577 about, I'm just going to write that many numbers until it becomes insignificant, and that's in feet. When it comes to rational root theorem, though, man, you have to plug in a lot of things. 750, like, I wonder what this graph looks like zoomed out. Let me zoom this thing out for 1 second and see if I see what other intercepts this thing hits, because it is a cubic, so it should be kind of going up and down a couple times here. So, I see it go up there. I don't know. I don't really see it hit at any other points. That really seems to be the only one that we care about. I'm sure there are other ones, given the rational root theorem, that it's possible we hit other guys. Sorry, I'm playing with this myself on this other side here. I don't know. Okay, that's the only one that's relevant to me, so maybe it's an irrational solution, or maybe that rational number is a crazy one. Factors of 750 over factors of 4. But I'm going to leave it like that. Okay. Maybe the other ones are complex solutions, actually, of course. All right, let's go to number 48. Thought-provoking. Write and graph a polynomial function of degree 5 that has all positive or negative real zeros. Label each x-intercept, then write the function in standard form. Okay, I'm going to do one with all positive. Actually, if they have all negative, then they'll be all pluses. So all negative might be better. So I'll do all negative. I'm not better, but I mean just easier to handle. So all negative. Label each x-intercept, then write the function in standard form. So write a polynomial. We can do, if they're all negative, we can do x plus 1 times x plus 2 times x plus 3. Let's do this. Let's do a squared one right here and x plus 4 like that. So there's a little bit to do here. When it comes to graphing this, because I'm going to try and keep the numbers smaller if I can, right? So what this will do as far as graphing is it'll cross -1 and -2 and -3 and -4. At -2, it's going to bounce off of it instead of kind of go through. It is a 5th degree odd leading coefficient, so it's going to start from the bottom and finish at the top. So it'll go maybe like this. It's going to have to bounce off that 2 like this before it goes back up through 1 like that. Now, I don't know what, I got to figure out what 2 times 3 times 4 or whatever is, or 4 times 3 times 4 is to get the true y-intercept, but that's an appearance of the graph, right? So when I expand this, they said write it in standard form, so we have a little bit to do here. They're going to make us do some work. It will end up being an x to the 5th, but let's see. I'm going to keep the x plus 1 as is for now. X plus 2 squared is x squared plus 4x plus 4. X plus 3 times x plus 4 is x squared plus 7x plus 12. I'm not going to do a box this time. I'm just going to work it out as it is. So I got x to the fourth plus 7x cubed plus 12x squared plus 4x cubed. Okay, I'm going to do this in silence. Okay, so there's this guy here. I still have to combine like terms, and then x plus 1 still has to multiply with this. So still's got a lot of work to do. Thankfully, they're all positive. I think, I think that's just going to help out a little bit. So 12, 40, 44. And then x is 48x, 28x is 76x, and plus 48. Okay, so now I got to multiply x plus 1 into here. At least because it's x plus 1, it doesn't really do much. It doesn't change the coefficients. It just raises the degree of these by 1. And then it rewrites exactly what's inside there. But then it has to combine with these guys in such a way. So this will be plus x to the fourth, 11x cubed. There's that 48, by the way. That was the 4 times 3 times 4 bit. So the final answer for this one, all positives in this case, will be x to the fifth plus 12x to the fourth, 55x cubed, 120x squared, 124x, and 48. Okay, so there is that guy, pretty massive when it comes to numbers, and with all positives, it helped me out just a little bit to do that. Okay, number 49, writing. The graph of the constant polynomial function f of x equals 2 is a line that does not have any x-intercepts. Does the function contradict the fundamental theorem of algebra? Explain. It doesn't. The fundamental theorem of algebra states that the degree of n has to be greater than 0, if you recall that. So, although it's a constant function, it doesn't do that. It does not contradict. Because it clearly states that the degree of the polynomial must be greater than 0. And f of x equals 2 is a polynomial. It's a polynomial, but of degree 0. So, therefore, we are all good. We are all good. Number 50. How do you see it? The graph represents a polynomial function of degree 6. How many positive real zeros does the function have? Negative real zeros, imaginary zeros. So it's a bit tricky just because of this bounce off thing right here. And this is what I was stating before. There's no telling whether this is degree 2 or degree 4, but it is an even degree. This is degree 1, this is degree 1. So for part A, it has one. So as far as positive zeros, we'll talk about that in a second. For negative zeros, there's something else. Now for imaginary, it sounds like they're assuming that thing's going to be degree 2. But there's one positive real zero here, and there's either 2 or 4 right here. I'm going to guess there are just 2. But so 2 plus 1 is 3. There are 3 positive zeros. There's 1 negative 0, and therefore 2 imaginary. It's possible in my head that there are 5 positives. If that is of degree 4, multiplicity of 4, I suppose. All right, use Descartes' Rule of Signs in your answers in part A to describe the possible sign changes in the coefficients of x. So given that there are 3 positives, that means that your original f of x has 3 sign changes, at least 3 sign changes, and that means by a multiple of 2. It can have 3 or 5. Here, I'll say this, 3 or 5. Let me just say that, 3 or 5 sign changes, because I'm still not convinced that it doesn't go up to 5, because it could to me. F of x has 3 or 5 sign changes. F of negative x has, it says possible sign changes. I don't know about the negative one. If it's just 1 sign change, or if it can have 3 or something like that, that part I don't know. I'm just going to say 1, 3, or 5. I don't believe that that's probably the case here. I think when it comes to seeing this as a whole, it probably would just have 1. And I think that's it. They said of f of x. They didn't say f of negative x. So I'm going to leave that just as it is. I'm going to say 3 or 5. It can't be 1, otherwise it couldn't have had 3 solutions there. But 5, I'd say, is still possible. I'm going to leave it like that. All right, number 51. Finding a pattern. Use a graphing calculator to graph the functions here. Compare the graphs when n is even and n is odd. I don't need a graphing calculator for that. I could do that myself. But let's see what else they say. Describe the behavior of the graph near the 0 as this increases. As n increases, use your results from parts A and B to describe the behavior of the graph here. Okay, I guess I'll use the graphing calculator to show you all of them at one time. It's something that I had mentioned before that, the multiplicities kind of show the graphs do one thing versus the other. So as I write this stuff down, let me just get them written as a whole. But f of x equals, we have, I'm going to kind of clone this and get this written multiple times here. F of x equals x plus 3, and then we're going to raise it to the second, third, fourth, fifth, second, third, fourth, fifth, sixth, and seventh power. So multiple here. I probably want multiple colors, 2, 3, 4, 5, 6, 7. So 2, 3, 4, 5, 6, and 7. And yeah, I suppose each one could probably be its own color. Basically, a lot of me just playing with my computer right now before we move on to the next set. So let's make this one blue, make this one green. Oh no, the 5 changed with it. What do I do? Make this one purple or reddish. I'll change the 5 in a bit. Make this one purplish. Make this one, what don't I have? Another kind of red. Ooh, that's a scary red. Orange. And let's turn that 5 into this color here. Okay, now when it comes to graphing, I suppose I'll pull out the graphing calculator thing in a bit, but here's the thing. The even functions will bounce off. First of all, -3 is the intercept here. Now, when it comes to it being squared, I mean, we should literally know that being squared even has the 1, 1, 2, 4, 3, 9 kind of thing. We could even get some aspects of the graph just based off this alone, right? This would be the squared one. Whoa, and it's going to curve back up and do that, right? It's going to bounce off of this thing like that. Now, the cubic, when you cube something, it's 1, 1, but 2, 8, like that. So it's going to go up a little more sharply. But when it hits, and it goes downward this way instead, it has the snake through. But when it hits here, and I wish I was more zoomed in, it's actually going to be a little closer. It's going to be a little underneath that graph on this side. So what I mean by that, and I'm going to show you in the graphing calculator here. What I mean by this is, and it might not be very apparent just based on these being so close to each other, x plus 3 squared versus x plus 3 cubed. I really got to zoom in on this part, though. I think that's going to be very helpful. So let's go from -5 to -1 on x. I'm really going to look at what happens in between here, from -2 to 2 on y. Let's see this zoomed in feature. So here's the parabola and here's the cubic. Whoop. Notice how it goes underneath right there. It has a more distinct, the curve, when x is between, or as x gets closer to 3, your y's get closer to 0 there. Now we can increase this. Let's look at to the 4th power. I don't know how good this is going to look on a graphing calculator with all these together, but to the 4th power, it's even going to be closer to 0 around that realm, and to the 5th power, even closer. Maybe we can look at ones at a time, something like that. So x plus 3, 6. Whoops, there's no plus. And x plus 3 to the 7th. Okay, let's just look at for a moment just x plus 3 squared and x plus 3 to the 4th. So as we see two things that'll be parabolic in nature, you'll see the 4th power goes a little bit sharper there. It's a parabola, but of a different ilk. And if we go to the 6th power compared to the 2nd power, even more so. It starts to kind of square itself off, almost look like right angle stuff, if you will. Here's the parabola, here's to the 6th power. So you see that sharper angling on it, right? So that's what happens as it gets deeper into those natures of the graph. Now that's true when you look at the cubic versus, say, the 5th power and the 7th power as well. Let's just do the cube versus the 7th power now that you're seeing the effect. So as n increases, as your exponent increases, as it gets closer to 0, you get a sharper effect. This person left another comment. So sharper effect toward 0 on those, right? It's more drastic. So I could draw all of them, sure, that's fine, but the bottom line is you're going to get that kind of effect to the fourth power. Again, it's taller in this case. Whoa, it's taller in this case, but it does get closer to this. I don't know why it's angling downward. I'm trying to go downward. It's going diagonally. It gets closer down like that, you know, right there, and so on and so forth. My drawings may not be perfect, but the graphing calculator is telling us what's going on. So compare them when n is even and when n is odd is part A. So part A, when n is even, it bounces off off x-axis. When n is odd, it snakes through, I'll just say snakes through the x-axis, if that makes sense, through your x-intercept. I should say x-intercept, not x-axis, but that's okay. All right, part B, describe the behavior of the graph near the zero, x equals -3 as n increases. As n increases, near the zero, the y values get closer to 0. That's where you start to see that kind of squared off effect that we said. It gets closer and closer to 0 as we go closer. Part C, use your results from part A and B to describe the behavior of the graph of g of x equals x minus 4 to the 20th power near x equals 4. So I'll say that first of all, the graph will bounce off x equals 4. And near x equals 4, we will have g of x will be approaching 0. Will be very near 0. See what's going to happen on a graphing calculator if I do this one, and we can go ahead and take a look at the effect of it. But what's going to happen on this one is I think this will pretty much just look like a right angle to us. If I go to the, and I'm pretty zoomed in as is, but if I clear these ones out or ignore them straight up. And again, someone left a comment on YouTube after this question. I'm going to go ahead and answer that one, pause the video for it. Yeah, interesting. Okay, so x minus 4 to the 20th power. So now I got to change my window range, and let's go from, say, 3 to 5, and say -2 to 2. I'm expecting something, whoopsie, I changed it on the wrong thing. 3 to 5. I'm expecting something that looks like it's going to go, it looks like it's going to go straight up into the x-axis. You're probably not going to see much of anything, and it's going to go kind of, it's going to go straight down and over and back up, kind of like that. It's not really going to have the parabolic shape just because 20th power is so incredibly sharp. Let's see. Oh, not quite as sharp as I expected there, but you can see you can't really see anything on the zeros there. Let me change the tracing a little bit here. Let me zoom out just slightly more from 2 to 6 so you can see the downward effect. And -3 to 3. Let's bold the curve on this, and let's see that effect a little more. So you'll see more of that straight downness, and it looks, and it hits -4 and kind of straight upness. It's not perfect straight downness and straight upness, but around 0 right here, because you're raising fractions now to the 20th power, which means it's going to get, instead, less than 1, closer to 0. That way, and that's what's happening there. So that's the effects, that's what you see, that's where it came from. Okay, let me pause and address this question. Okay, let's move forward. I feel like I'm not going to answer any more of those questions from YouTube. I want to keep going on this video. Again, when it pauses, you guys don't care. The pause means nothing to you, but it's kind of an inconsistent flow for me, so I'm going to go. All right, let's look at number 52. Find the zeros of each function. Hey, that's like 4 parts. All right, f of x equals x squared minus 5x plus 6. Okay, at least this one's easy. So this factors into x minus 2 times x minus 3, and that equals 0. So x equals 2 and x equals 3. Okay. Next one, g of x equals x cubed minus 7x plus 6. Well, rational root theorem says plug in a value for x. We can try 1, and 1 will work. So when we plug in 1, we get 1, 0, -7, and 6 used on synthetic division. And we'll have this. So this becomes x minus 1 times x squared plus x minus 6. X squared plus x minus 6 factors into x plus 3 times x minus 2. So this is x equals 1, 2, and -3. h of x equals x to the fourth plus 2x cubed plus x squared plus 8x minus 12. Let's go for factors of 12. Let's try 1. 1 plus 2 is 3, plus 1 is 4, plus 8 is 12, minus 12 is 0, so 1 works. Once again, synthetic division on this guy. 1, 2, 1, 8, negative 12. Hopefully you know how I do that kind of at faster speed at this point, once I've established what my number is that works. This is factorable by grouping. So we have x minus 1 times x cubed plus 3x squared plus 4x plus 12, set it equal to 0. I think at some point we got to set equal to 0 to anyway. I probably should have been doing that on these ones. Equals 0 equals 0. So let me get rid of this really quickly here. So equals 0. So factoring by grouping, if I factor out x squared, I get x plus 3. Factor out 4, I get x plus 3. And this one, x will equal 1 and negative 3. Subtract 4, take the square root. It's plus or minus 2i. 2i, negative 2i. And then the last one here, we have k of x equals x to the fifth minus 3x to the fourth minus 9x cubed plus 25x squared minus 6x. There is a common factor of x. And you're left with x to the fourth minus 3x squared minus, or cubed, minus 9x squared plus 25x minus 6. All right, 6 is your constant. By the way, unless you factored out that x, that 6 wouldn't have been a constant. So when it comes to rational root theorem, you ain't choosing 6. So now we can choose 6 on rational root theorem and go to war on that. Try and plug in 1. I don't think 1's going to work. Negative 1, we get 1 plus 3 is 4, minus 9 is negative 5, minus 1. No, that doesn't work. 2 is 16, minus 24 is negative 8. Minus 36 is negative 54, plus 20, plus 50 is 6, minus 6 is 0. I think 2 works. So when we do 2 on this one, we get 1, negative 3, negative 9, 25, and negative 6. Okay. Okay, that does work. Now, it doesn't factor by grouping yet. X minus 2 is this guy. And here's the other guy set equal to 0. Let's try 2 again. Remember, 1 and negative 1. Oh, actually, no, 2 won't work here. Only 1 and negative 1, 3 and negative 3. We already saw 1 and negative 1 wouldn't work, so only 3 or negative 3 could now work. Those are the possibilities. So let's try 3. 27 minus 9 is 18. Minus 33. No, that's too big. Negative 3. Negative 27 minus 9 is negative 36. Plus 33 is negative 3, plus 3 is 0. So the last one, last resort, negative 3 indeed worked. So 1, negative 11, and 3. And we get that. And, okay. So x minus 2 times x plus 3 times x squared minus 4x plus 1. This quadratic is not factorable. I can solve, say, by completing the square. I'm going to add 4 to both sides of this. I subtracted the 1 over. This is not imaginary solutions, though. These are real. X minus 2 squared equals 3. Take the square root of both sides. Excuse me. Take the square root of both sides. And you get x minus 2 equals plus or minus root 3. So x equals 2 plus or minus root 3. Now those are two answers. So are x equals 2 and x equals 3. Okay. They're all solved. Jeez, man. That's a lot. And that's not even part A. That just says find the zeros. Describe the relationship between the sum of the zeros of a polynomial function and the coefficients of the polynomial function. Is there something to that? All right, let's see. The coefficients here are 1 minus 5 plus 6 equals 2. And here 2 plus 3 equals 5. Is that what they said? The sum of the zeros of a polynomial function and the coefficients. Oh. And the coefficients. They didn't say the sum of the coefficients. 2 plus 3 is 5. 1, negative 5, and 6. 1, 0, negative 7, and 6. 1 plus 2 is 3 minus 3 is 0. Okay. 1, 2, 1, 8, negative 12. And 1 minus 3 is negative 2. The plus minus 2 cancel out, so that doesn't matter. And is this a different question? That's the same question. Where's K? Here it is. Oh, that's K. I thought that was an H. 1, negative 3, negative 9, 25, negative 6, and 2 plus 3 is 5. 2 plus or minus root 3. The plus or minus root 3's cancel, but the 2's add. Plus 2 plus 2. 5, that's 9. There's a 9 here, and that's a negative 9. There's a negative 2, and there's a 2. I don't know. There's a 0, and there's a 0. There's a 5, there's a negative 5. I don't know. The middle term has the opposite. There's a middle term. Is it always the second term? Negative 5's no. This one was the third term. What do they want? A middle term is the opposite of the sum of your solutions? That's all I'm seeing. I'm not sure what the answer is, unless we're supposed to add the coefficients together, but I didn't see anything there either. One of the middle coefficients is the opposite of the sum of the solutions. That's all I see. Remember, one of them was 0. The opposite of 0 is 0. That's all I got. I don't know if that's right or not. That's as best as I could find, man. That seemed a little different of a problem. Do you guys see anything else there? I mean, it's something, maybe there's something I'm not noticing. What do they want? I have no idea what they want for that problem, guys. Describe. Oh, the product of the zeros. Why did I think they said sum of the zeros? Oh, right here, because part A. I'm sorry. Okay, part B is the product of the zeros. Okay, good. Okay, because I saw the product of the zeros. I'm like, okay, interesting. So I'm seeing the opposite effect. I'm seeing that this is a middle term. It's the second term. And that's the opposite of that. And all the other ones, notice how this one, the negative 2, this is negative 2 by the sum of those, and that was the second term there, the opposite of that. All of them seem to be the second term. This one did not seem to be the second term, though. This had 2 plus 3 is 5 plus 2 there, whereas this originally, that is a negative 9 there. That's the only one that doesn't seem to be that opposite. Oh, I'm sorry. That's not 3. That's negative 3. Let's do that again. This is negative 3. 2 minus 3 is negative 1. Plus 2 is 1. Plus 2 is 3. And that matches with the negative 3. Okay. So, that does seem to be something here. So, sorry about that mess up there. It's probably because it was just so far removed. So, that is 3. It's not one of the middle coefficients. The second term, it's not always second term because, it's second term, but remember the one that we called 0, what was the one that was 0? 0 right here, keep in mind, the second term to us is negative 7x. So the term after, let's see, not the second term. The coefficient of if your polynomial is of degree n, the coefficient for the n minus 1 term, how about that? For the n minus 1 term is the opposite of the sum of your polynomial solutions. That's as best as I got. It looks to be repetitious there. It definitely does seem to be there. All right, part B asks about product. Part B I could answer. Describe the relationship between the product of the zeros of a polynomial function and the coefficients. On part B, here's all I'm going to say, and this you guys should know this pretty well as well. Well, maybe. It depends. This 2 times 3 is 6. This number is 6. I guess I got to write them. 2 times 3 is 6, and that number is 6. Here, 1 times 2 times negative 3 is negative 6. Now I have to question whether my thing's here. 1 times 2 times negative 3 is negative 6, and that number is, I guess that number is still positive 6. What I was going to say about these were the constant is the same as your solution bits. And now I need to make sure these signs are correct, because they should be, because I felt like the product should just be equal to the constant term, right? If this was a 6, 1, 2, negative 3. Well, that's a negative 6, and that's a positive 6, so I got to rethink that when I talk about that answer. This one is 1 times negative 3. 1 times negative 3 is negative 3 times 2i times negative 2i. So this is negative 4i squared, which is positive 4, times negative 3 is negative 12. That's negative 12. This was negative 12. So that's in line. And then this last one right here, we have, I don't know, 2 plus root 3, 2 minus root 3. 2 minus root 3 is 4 minus 3, which is 1. So 1 times 2 times negative 3 is negative 6. And this was negative 6, well, when factored on that part there, right? So, we missed an x here. This x was 0. This x was 0. X equals 0 was another solution on this. Shoot, I missed that one as well. Darn, I'm missing everything here. Anyway, that x was 0. Well, 0 times all that's 0, which means the original constant is 0, so that seems to make sense as well. The only one that's not in agreement is the second one. I want to make sure I copied down the problem correctly. X cubed minus 7x plus 6. I did copy it down correctly. Let's make sure the solutions are good. I got a 1 thing, so x minus 1, so 1's a solution. They added to 0 like the second term was 0. That was all good. 1, 2, and negative 3. 1 times 2 is 2 times negative 3 is negative 6, and that's positive 6. That's the only one that doesn't seem to be perfect with it. I feel like it should have been. Maybe it's because this x minus 1 was already factored out. I don't know. But otherwise, it seems to kind of repeat that pattern. But the product of the solutions is equal to the constant term. I'm missing something with that second one. I don't know what it is, and I'm having trouble with it. And the thing is, I put so much pressure on myself making videos with these things because they're live. They're not live, but they're affixed as they are. They're permanent and they can't change. And I talk through these things. If I did it by myself, I would figure it out the right way. Here I feel like I'm in a rushed mode and I got to talk through it. And there's something there that I'm missing and I can't tell what it is. I'm going to do one more brief look over and see if I can find it. This all came out the right way for synthetic division purposes. That's a minus 6 there. I see that's a minus 6. 1, negative 3, and 2. X plus 3, x minus 2. I'm not seeing why that's a negative 6 and that's a positive 6. All the rest seem to pan out exactly that way. So, Let me make sure on those ones. 2 times 3 was 6. Yep. I don't know. I'm going to leave it. It's close enough. I believe it's supposed to be that. All right, number 53. Problem solving. You want to save money so you can buy a used car in 4 years. At the end of each summer, you deposit $1,000 earned from summer jobs into your bank account. The table shows the value of your deposits over the 4-year period. In the table, G is the growth factor 1 plus R, where R is the annual interest rate expressed as a decimal. Copy and complete the table. Okay. Copy and complete. Okay, so as far as I'm concerned with this, we're just filling those things in with the same amounts of multiples, meaning that we, add these g's and g squareds and things like that. So 1000 g, as we do another g in here, 1000 g squared like that, and 1000 g like that. In these deposits, we haven't had any money yet deposited in there, so that's kind of the first part. All right, so that's part A. Part B, write a polynomial function that gives the value v in your account at the end of the fourth summer in terms of g. If year 4 is the fourth summer, we can add all those together. So B, this is part A. Part B, V, values V. So V equals 1000 G cubed plus 1000 G squared plus 1000 G plus 1000. Seems like I really want to factor out that 1000, but that can be an answer. Part C, you want to buy a car that costs about $4,300. What growth factor do you need to obtain this amount? What annual interest rate do you need? So is this anything, is V in thousands or anything like that? V, okay. So 4,300 is the value, and we have this information here. It's one of those things where I don't know if I'm supposed to use the calculator or not, but I am going to subtract 4,300. So I get 1000 G cubed plus 1000 G squared plus 1000 G minus, now this is 3,300. Equals 0. I can divide everything by 100 at the very least and get 10g cubed plus 10g squared plus 10g minus 33 equals 0, and we can solve from there. Now, I think this is one of those calculator usage things. I can't guarantee that this is a rational solution, so I'm just going to go to the calculator for that part. So let's do that. Let's do 10 to do cubed. Okay, let's get a reasonable window range, just kind of square it off again. What are we looking for? Growth? Oh, it might be a decimal or something. Let's see what this does. Okay, it shoots up right there. Okay, let's see what this thing's crossing at. Right of 2. Okay, it's crossing at 1.04 something, so G is about 1.04848182. I'm just going to write that. That's our growth factor of that value right there. Got a G of about that, sure. Now, ask what's R. Now, R, where is it? G is 1. In the table, G is the growth factor 1 plus R. So G equals 1 plus R. 1 plus R equals 1.04848182. So R is 0.04848182. Now I'm going to kind of get these answers a little bit different. So this G is about 1.048. How about like that? R is a percentage, right? It's about percent. This is about 4.84%. Oh, let me put a 4 here. 4.84%. So that's what we're going to get out of that. So yeah, I'm just using the calculator at that point. It's kind of one of the more complex questions with the numbers. All right, that's, whoops. Oh, that's it. I thought we were going to number 65. Guys, that ought to do it for this one. What a nice surprise. I thought we still had up to number 65. That must have been the last problem set that we did. That'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. That was the best surprise I've ever had. I was like, I still have 12 more problems to do. I got a lot more things to take care of. Take care, guys. I'll see you in the next one.